is required. Why they are saying it as coefficient of determination? Why they are determining which is your best model? You're determining which is your best model. Okay. With the help and of how you're determining, you're determining comparison with the and average. How you're determining, no matter what line you predict, the average, no matter what line, no matter what line you predict, if you are able to look no at matter what line you're able to say that you
إذ جاءهم فقال
important this. What is collinear? Linear. If a point lies on the same line as that of the other, this is the line. Okay. These 2 points if a point lies on the same line as that of the other, this is the line. Okay. These 2 points are collinear. Okay.
Lying on the same line. So when I say multicollinearity, it shouldn't be present. Meaning, if you have feature 1, you have feature 2, you have feature 3, you have feature 4, and so on till feature n. They should not be giving the same information. Meaning,
they shouldn't be collinear amongst themselves. You are predicting target 1 using feature 1 to feature 2, feature n. This is your, and you're predicting target. The relationship between feature 1 and feature 2 shouldn't be linear. Okay. Meaning they shouldn't be on the same line. What is the example? In the car example that we were looking at, when you're trying to go and
sell your second-hand, you're trying to sell your car in the second-hand market. If I say car's age, okay, and number of years since you bought the car.
Isn't they the same thing? Correct? They're telling you the same thing, right? If you purchased a car, purchased in what? 2020 was a really wild year to purchase a car since we were in COVID. But anyways, if someone did, okay, what would the age be? Age would be 4, and number of years since you bought would also be 4. Correct? So they're giving the same. It is basically just a different name, but they're giving the same information to the model. No additional information is being given. Okay, cool. Then the third example is that your errors. Okay, I'm saying errors, but when you look at the literature, they will say residuals. And you know what errors and residuals are. They are one and the same thing. Residuals should be forming a normal distribution. Okay. If you go and plot your errors, okay, they should follow this kind of a curve. Okay. They should be normal. Very simple, right? Cool. Then what is the fourth one? This is something that people ask. Okay. That's why I'm putting a star mark. Not because it is different. It is very easy. It's just that the name is really different. Okay. And they try to test whether the person has this knowledge or no. Okay. So it is what? That your error should be no heteroscedasticity. Okay. No heteroscedasticity in errors. Or in other words, it should be homoscedastic. You get the gist of it. Okay. Now, why they ask is because this heteroscedasticity and the homoscedasticity doesn't, really understand. People don't understand it really well. So what happens is you understand the word hetero and homo. Homo means same. Hetero means different. Okay. Homogeneous mixtures and heterogeneous mixtures. Now, if you fit a line, okay, your variance should not be like this of your data set. This is your data set. Okay. Let me make it more clear. As and when this is increasing, okay, this is increasing. This is also increasing in different proportion. The variation is really different, right? This is not required. This shouldn't be the case. This should be the case. Okay. It should be equal on both the sides. Okay. This is heteroscedasticity, and this is homoscedasticity. See, it's difficult to say also. This is what you're looking for. Okay. And the last one is autocorrelation. When I say autocorrelation, there shouldn't be any autocorrelation or no autocorrelation. This is mostly related to the time series kind of data because that tells you, that was, if you remember in the first session, I told you there is a difference between regression and time series, which is different. and is very minute. You need to remember it. It is time based and it is not. Regression is not time based. Time series data is time based. Okay. Now here, what do I mean by autocorrelation? Correlation, you understand, there is some correlation. If you break the word, auto in this context means with itself. So previous values should not have relation with future ones. In other words, future values, this I'm talking about the target, okay? Target. Your future values of the target should not depend on previous values, previous or past values. Okay. With this, linear regression is complete. There is n number of, text or literature that you can refer.
There are many different types of regressions as well. Linear regression itself, go and explore it. Okay, I highly recommend that you go out of your comfort zone, go and recommend it. You have the base now really strong. With these sessions, your base is really strong. The more you explore, the more it will become beautiful. Your knowledge will become beautiful, and the interview will be like, yeah, this guy knows basics so good, and then he knows all the varieties also. There are small minute changes, and they call it with a separate name. Internally, this is what is happening. Okay, perfect. So this was linear regression. Now we are going to start with logistic regression. Okay, now what is logistic regression? It is a classification type. It is classification type of an algorithm. Okay, target variable is how? Target variable will have categories. Okay, it is either 0 or 1. Example would be spam or not spam. Okay, this is an example. Okay, now let's look at some theory around it. Let me introduce you to this. Yeah, now we looked at machine learning. We talked about the third also, which was what? Reinforcement learning, right? But I told you 90% of the times you will be working on supervised. Okay, now we looked at the supervised first, we looked at regression, and we looked at linear regression, right? Now we are looking at classification. In supervised, when I said supervised, it is based on, supervised is based on label data. Okay, it should have label. So in classification, there are two things. One is logistic regression, which is what we are going to study now. And there is another which is called SVM. SVM is nothing but very popular classification model and has been since for a long time. I have personally used it a lot, and it stands for support vector machines. Okay, really beautiful concept. If you go into the depth of it, really mind-blowing how these statisticians and these people who were doing research, they came up with these examples and these thought processes. It's easier to understand, but when you have a blank slate and you have to come up with this, it takes some courage. That's why they are there and we are not there. Okay, but we are learning from them. So logistic regression is a classification model based on statistics. Okay, deals with categorical target variable or dependent variable. Okay, could be binary or dichotomous. Now binary, you understand binary. Dichotomous is same as binary. If you don't know the meaning of it, it comes from biology kind of, you know, perspective, since they were researching it. So it's just stuck with this algorithm. Just keep that in mind. It works on dichotomous variables or target variables when the output is 0 or 1. When I say 0 or 1, not literally 0 or 1, it could be 1 or 2 also. Depends on how you're coding your target variable. Okay, but there should be only two categories. Okay, there should be only two categories. Multinomial, I'll touch on that, but just say that, you know, it could follow anything. It could follow anything. There could be multi this thing, you know, nominal and this thing. There could be many. Just ignore that point for now. We'll touch on that. Okay. Now takes both continuous and discrete input data, meaning your independent features can be either continuous or can be discrete. Okay. There wasn't any discrimination in linear regression also, correct? You could do anything, and here also there is nothing in independent features. There are certain algorithms. Why it is necessary to put that out? There are certain algorithms that work on all these kind of things. They work on discrete also, but the way that you have to put that information inside the model needs some modification, needs some, when I say modification, needs some encoding. Okay, like for example XGBoost, we are going to look at decision trees, random forest. Okay, some of them, they need different kind of modification of the discrete type of values before we apply the model. That is why it is kept there. Okay, so regression is
The one where you are predicting your continuous variable. So regression, your target variable will be continuous. Meaning like predicting what? House price. It can take any value, no? 100,000, 10,000, 1 lakh, 20 lakhs, 20.22 lakhs, whatever. Predicting car price. Okay. And what was classification? You need to classify it, either this or that, or out of many things. So remember, we looked at these two examples. Your target variable is discrete. When I say discrete, it has one or the other, meaning you'll understand from the example. Spam and no spam. Either it is spam or not spam. Correct. The other example was where you guys looked at my beautiful drawing, fruit example. Now we looked at in the concept of clustering, unsupervised, but you know there are three: apple, banana, and orange. You have only what? Three categories. You're providing the features and you're also labeling. Given the label is there, then it becomes a classification problem. The other example, okay? The other example would be, now you have cars, correct? I'm relating it with this so that you're able to understand. You have cars. Here you're predicting the car price, but if you had to predict the type of the car, now the car can be what? Car can be an SUV, higher segment. Then it could be a sedan. Okay. It could be a hatchback. Correct. So these are different types. When you are given this data, car type, and let's say you are given engine, okay, what else, seater, ground clearance, meaning how up it is, ground clearance, whatever, okay. And you are told this is an SUV, this is a sedan, this is a hatchback, and whatnot. This is your target variable. Okay. So your target could be, depending on all the features that you have, it could either be SUV or a sedan or a hatchback. You have only three options. Options is not the right word, but for understanding, I'm saying three options, but you should always say three categories. Okay. So now you understand what is classification, but your logistic regression works on only binary. Binary output. Only two. Logistic regression will work when you have only two categories in your target variable. Okay, I'll have to slightly digress, but let me explain this. This is important for understanding. Now, tell me one thing. Tell me one thing. When you say hatchback or when you say SUV or when you say sedan and you pass it to your algorithm, which is on your laptop, okay, it will be like, what are you saying? Will it understand hatchback, SUV, sedan? No, right? What does computers and everything that you work on digital, they understand based on numbers, bits, binaries. That English is our language, Hindi is our language, this is our language. These things, they don't work on machines, they don't understand that. Okay, so what happens is, on the same data set, you are encoding it. Okay, I'm not putting in the additional columns, but you get the gist of it. Let's say this is car type, this is hatchback, then sedan, then this is SUV, then hatchback. Okay, what you are doing is you are saying, whenever I see a hatchback, I will put 0. Whenever I see a sedan, I will put 1. Whenever I see SUV, I will put 2. Okay. This concept is called what? Encoding. You are encoding it for the machine to understand it. It will not understand what is hatchback, SUV or sedan. It will just say that all the zeros are separate, all the ones are separate, twos are separate. Okay. These are three categories. Now, when we do it on label, it is called label encoding. Okay. There are different types of encoding also. We'll cover it into the future, but there is something called as one hot encoding. Okay. Then there is TF-IDF. Norm frequency and inverse document frequency. This is the concept of NLP. Let me relate this with a really good example, which everyone must be using. Okay. Everyone has looked at ChatGPT or understands what ChatGPT does, correct? You are typing in words. But it doesn't understand the words. Internally, what it's doing is, it is doing this encoding. And over there, the concept is called embeddings. There is way further or of much detail, concepts there, which also say tokenization and embeddings, and there are many things. But did you understand? It is not non-numeric. Okay, it is not non-numeric. You are, no matter what you're getting, you are doing some kind of encoding for it to be understood to your machine. Okay, perfect. One hot encoding, it is this. One hot. This all concepts are coming from the English speaking community. So one is one, hot is nothing but zero, 1 0. Okay, it is nothing but 1 0. This we'll learn in decision trees and random forest, but this is how you're encoding. Okay, perfect. So we just introduced logistic regression. Okay, it works on binary output. Then it is a classification type. Your target variables will have categories. Actually, in fact, these two should be same only, but I'm just connecting it here. Okay. And then this is your example. Okay. Then we looked into a difference between regression and classification. We covered it here. Then to answer a query around non-numeric data, to have that intuition and understanding correct, it is not only non-numeric, it is also, we pass all the non-numeric or anything textual thing by encoding it, because that's how the machines understand. Okay, cool. So here, some of the use cases. Let's look at some of the use cases. Okay, so now Olympics is going on, correct? Olympics is going on. So let's take an example from Olympics. Let's say Neeraj Chopra will win or no. I hope you know who Neeraj is. He's a guy, okay, with long hairs who throws javelin. Okay, this is my javelin and this is the field on which he throws. Okay, he's an athlete, Indian athlete. He won gold last time. So we are saying what? We are saying win or lose, right? This is what 0-1, correct? The other example, World Cup. Will India win? Yes or no? There is nothing in between, right? It's clear. Either we will win it or we'll lose it. We are not going into the rankings that they'll reach semi-final or no. Our motive is only to say whether we are going to win or lose, yes or a no. Okay. The other example, we have been looking at it. Email. Spam. We say it's spam, not spam. If you ask a question, is it spam or not spam? Again, the answer is yes or a no. Correct? Fourth, is the cat fat? Yes or a no? Outcomes in all these use cases, whenever your outcome is either this or that, binary output, that's when we use logistic. Okay. Now some of the real world examples. Imagine, okay, you are the owner of Geo Cinemas, for example. Okay, you're pretty rich, but still, you are the one who is responsible for getting the profits. Okay. Now you need to know using machine learning. This is an actual real world example. Can you predict whether a customer is going to churn or not churn? Customer churn. So this is how churn means whether uh, they are your members. Okay, you've paid, you've taken the prescription subscription, sorry, of that, Geo Cinemas, Netflix, whatnot. Okay, are you going to churn? Meaning, will you leave? Will you stop your subscription? That is called churn. And when you do this for the customer, you mean to say whether you're going to churn or not churn. Okay. So this is for anything. Could be Netflix. Okay. Could be Geo, could be Hotstar, anything. Okay. This could also mean for a in US there are these Walmarts. Okay. Here we have D-Marts, Walmarts and D-Marts. You need to know if your customer is going to churn or not churn. Okay. You must be using some Wi-Fi's, whatever brand, let's say Airtel or Geo Fiber. What else? Who is there? Oh, Act. Correct. All these folks, they need to know whether their customer is going to churn or not churn. Meaning, are they going to stop their services and not renew it? This is a big problem, guys. And if you are able to identify this with high level of accuracy, you can stop the customer from churning. You can give an additional discount, an additional something, okay, that will stop the customer from not renewing or going off your platform. The other example would be Swiggy or Zomato. So Swiggy would like to know whether a person who is ordering from me today, tomorrow, from next month onwards, okay, is he going to churn? Mean, is he going to stop ordering from me? Not completely. Probably what do you have? That Swiggy Super is there, no? And Zomato Gold is there. So is he going to stop using that and switch to Zomato, or not going to switch to Zomato? I don't care. All I care about is he or she going to stop my service or not? Is he going to churn? Is he going to switch? Why is this such a big problem? Big problem, because customer acquisition is really high. Customer acquisition cost is high. They want to, so to make you the customer for the first time, they have spent so much of money. They have given you marketing on the TVs, on your phones. Okay. They would have, have one person calling you, not directly for you, but they're spending on their ads, right? You must be seeing these people, they put really big banners on the roadside, correct? They also give some TV commercials, TV ads. Then they also sponsor some of the teams in tournaments, correct? So they're spending for what? So that people see that what is, if there is a person who doesn't know what is Swiggy, okay, and really likes food, if they know that there is, through these advertisements, they know that okay, there is something called a Swiggy. Out of curiosity, they'll be like, yeah, I'm seeing this everywhere, who is this Swiggy? If they search, and they're like, "Arey, he's giving me free home delivery and all. I'm sitting at my home. He'll give me, food that I've ordered, and I have so many options." All these things are on convenience, right? It is for the customer's convenience. You're getting food at your home. You are able to order something which is 20 kilometers from your house, okay, without going there, and you're still getting that whenever you want when you're ordering. So everything of this is on convenience. So if a new customer looks at it, they most probably will find it convenient and they will enroll into Swiggy. And then it is Swiggy's different game of marketing. First thing is to acquire the customer. And to acquire the customer, once it has become my customer, now there is a different game altogether. It is called CLTV, which is customer lifetime value. There is a journey that a customer takes in the business. Okay, read about it. It is an interesting concept. How people think about it. Read about it whenever you're free. Okay, so this customer churn is really important. So they need to find a way that I can predict which customer is going to churn. Is going to churn. And when you say churn, ML models, they don't work on 100% guarantee, right? Even with linear regression, we knew we are predicting and there could be some errors. So they work on what? Probability. This is in the first class I told you. It is 1 minus 1 game. Correct? They tell you this is the probability of a customer to churn. Let's say if the probability is 0.8, meaning 80% it is going to churn. Not it, that person is going to churn. Customer is going. Then can I also say 20% no churn? There's a 20% probability that it will not churn. Correct? It is 1 minus 1 game. It works on probability. Okay. Now these are some examples that we looked at. Now in linear regression, what we were doing, we were fitting a line. Now if you look at a data for classification, how will it look like? Okay, let's take an example of email, spam and not spam. Okay, because it is an easier example to understand, and same is, we can apply it to anything. The idea is to understand the concept. Okay, this I am saying, I'm going to say that they are spam. And here on my y-axis, I have all the ones which are not spam here. Okay. And there are a few keywords. Remember, it is going to look at the patterns, and keywords would be what? Keywords, if in the mail content, these keywords come, you are able to say whether it is a spam or not spam. If it says lottery, correct? Win, prize, jackpot. If these keywords, these words are present in the content of your email, this means that it has a high possibility of being a spam. More these words, higher is the probability. If in an email I see there are, three of them coming, three of these keywords coming in one email, three keywords present versus another email in which one keyword is present, which has a higher possibility or a probability of becoming spam or being a spam mail. Let me change this to 3 to 8. If 8 keywords are present versus 1, right? The one which is having more number, correct? Everyone with me, right? So this is going to have higher probability. This is going to have a lower probability. This is going to have a higher and this is going to have a lower. Okay. Now, let's say here are your number of keywords. Number of these keywords on your y-axis. Now let's say this is 1, 2, 3, 4, 5, 7. Okay. This is how it is. Let's say an email that has 4 or 5 keywords. Let's say 5. It has 5 keywords. Am I not going to say that it is a spam? Correct. The one with 6 can also be a spam. 7 will also be a spam. Okay. There could also be instances where when I see only one keyword and it is not a spam, 2 keywords, it is not a spam. Okay. Sometimes there might be 3 keywords and still it is not a spam. And vice versa can also happen. There are 2 keywords present there. Someone is really sharp. They've taken only 2 keywords, but still it is a spam. Okay. An example would be, hey, you have been shortlisted by KBC. You have won lottery of 10,000, 1 crore. I used what? 1 and lottery. But this is a typical spam email. WhatsApp pay now these days they send you a lot, but do you agree? There are some exceptions. Someone can be really sharp and just use only one word so that even they know that someone who's reading this content, the whole idea is that they should click. Once they click, enter their details, then gone. Money is gone. Your hard-earned money is gone. So this thing can happen. Similarly, there could be, a genuine email which has 5 keywords, but still is not spam. Your friend has sent you this email saying that, hey, what? Hey, Anil, I am really happy to say that, I have won a lottery and the prize money that I'm getting from it is, let's say 50 lakhs. I think I have hit a jackpot in life. I've used all the words. But this, your friend has sent you. He's not asking you to, press on any link or anything. So it is a genuine email. So this case and this case, you understood, right? There are exceptions. Now, since we are able to do this, whether this is a 0 or 1, okay? Now let's say I am saying when it is a spam, understand the concept. I told you that when you have to encode it. I'm saying the spam is 1 and not spam is 0. Okay. All the spam in your y-axis, you have either 0 or 1. Earlier you were having what? Continuous variables, continuous values. Now you are having only 0 to 1. And there are only 2 values that it can take, either 0 or 1. That we know. For logistic regression, that is the case. Now, the concept is same. We have to fit the line. But can I fit this line? Can I fit this line? Or this line? No, right? I cannot. Which is the line that I need to fix? Okay. The line that I can fit could be something like this. Could be something like this. It looks like an S, correct? So that you're able to classify all these correctly. This one, this one, this one, and this one, this one, this one. You're able to classify it correctly. This one you were not able to, this one you were not able to. Here, the line is not going to be a straight line. It is going to be a curvy line. Okay. So now you have a data set. Now you have a data set. One email. This is one email. This is one email. This is one email. Okay. You are trying to fit the line on the entire data set. Over there in linear regression also, we were trying to fit the line in the entire data set. This is your entire data set. All the emails together. How many do I have? I have 8. Let's say you have 8 emails. Okay. The best line with which you can reasonably fit is that you can correctly identify 3 here and correctly identify 3 here. 3 in spam, 3 in not spam. But you're not able to identify this correctly, this correctly. Why? Why? Because same concept as that of your linear regression. Now, if I go, this is my line. This yellow is my line. Let me draw this properly. Okay. This is my line. Now, whenever you are trying to in linear regression also, what we were doing, when I have to look at something which is at having 2 keywords, I used to plot it on my line here, and then look at its value on the y-axis. Everyone with me, do you understand misclassification? This one and this one are your misclassifications, correct? And this one and this one, all these are correctly classified. What we are trying to achieve here is we are trying to fit a line such that our misclassification is less. Okay. In this case, when there is a 0 and a 1 output, you cannot fit a straight line. It has to be a curvy line. Now the curvy line is this type of a line that we are able to fit, which is S shape. Okay. This is what? S shape. Okay. And the motive is similar to linear regression, that your error should be minimum. Here in this case, the misclassification should be minimum. Okay. Cool. The other example, the other idea is that here on the y-axis, you have 0 to 1. Okay. Doesn't it tell me that it is the probability? Somewhere in between, this is 0.5. If there is a value that is coming here from out of this one, anything greater than 0.5 is going to be spam, and less than 0.5 is going to be not spam. Correct? Based on this curve, based on whatever plot you do here, anything, if I plot it on my y-axis, if it is greater than 0.5, it is going to be spam because it is closer to spam. And anything which is less than 0.5 is going to be not spam. The chance of it being a not spam is more because it is closer to the one where it is not spam. Okay. Now this 0.5 is also called a threshold or a criteria. This you have in your hands. Depending on use case to use case, you can either take it as 0.5 or 0.7 or 0.4 or 0.6. I don't care. Depends on the use case. You have this in your hand, looking at the data. Okay. And all the values here in between 0 to 1 can take any value. Now you understand, since this is 0.5, it can take even 0.0002. It can also be 0.112. It can also be 0.234. It can also be 0.67. This is nothing but this is probability. This y-axis is a probability. You have this data. Okay. Okay. Now you have this data set with you. Is the same thing correct? Let me clean it a bit. It is the same thing that we plotted above. Now tell me one thing. Are you able to see that in this yellow line, this is not present? And in this yellow line, this is not present. If you try to plot, let's say I have 7 here. I had 7 here, right? If I plot the number of keywords in an email, if 7 are present, if I try to plot it here, will I not touch the line here? So what does this value have here? It has what? It has 1, which is nothing but spam. Okay. So now here, when you are at 2, you are trying to touch the line, your line that you have fit. And when you try to plot it on the y-axis, it is what? It is, let's say, 0.01. Here is your 0, and here is your 0. And this is what? This is not spam. Correct? And you're going to say, this is 0.5. Your criteria is any probability in this line. If it falls anything between this, I'm going to say it is spam. Meaning anything, if the probability is greater than 0.5, it is going to be spam. And if it falls in this region, which is less than 0.5, it is going to be not spam. So this one, rather than calling it as an error, you are not able to classify it correctly, na? It is spam, but you are still saying that anything which has 2 keywords is going to be not spam. But this is spam in reality. This is your error. And error in classification is called misclassification. Okay. So in general, since this is probability, in general, threshold as a thumb rule is chosen to be 0.5, 50% here, 50% there. But depending on your use case, you can change that value. It is in your hands. It is in your hands, depending on what you're seeing in the data. Let me give you another example. So that you understand this threshold thing. Okay. Now, imagine another use case. You are working with HDFC. Okay. And I come to you and I say that, can you give me a loan? So what do? What is your problem? Understand this. Your task is, should I be given? Okay. Since you are going to read it at your end, should you give loan? That is your problem. Correct? That is your use case. That's the you want the solution for this. You mean the other way to look at it is, if I am coming to you, okay, let's say this is who is asking for loan. Okay, asking for loan. You need to say whether he or she is a fraud or no. This is what? Another example of 0, 1. Yes or no? Correct. So here again, logistic regression will come. But tell me one thing. Out of, let's say you receive 100 applications. You receive 100 applications. How many of them are fraud? Only 1%? Or in, imagine we are living in a really bad country. even then, this would not be more than 5%. Terms and conditions applied on the country, as in, depending on the country, it might be 10% also. But in my experience, this is really huge. Even 1% is really huge. Okay. Now, this is also called as imbalanced data set. Imbalanced data set. Here, out of the 100, 95 are not fraud. Okay. And only 5 of them are fraud. Now, in this case, do you think 0.5 will be a good choice? No, right? No, right? Now you understand how you need to put it really tight. That threshold should be really tight, meaning that 95% of the times I don't get a fraud application. There's only 5% chance. So this line here, this threshold here will not be 50%. Correct? It will be somewhere here. Okay. So that's how you change your threshold. And that's why you have it in your hands. And that's how it depends from use case to use case. Understood? Is that clear? All right. Okay. Now you know this. And now you know that it is an S shape. Now, did anyone tell you, or do you know why S shape? Why only S shape? Why cannot I put a Z shape? Why cannot I put a C shape or an invert C shape? Right? All these are possibilities, right? If I put a graph here, all these are possibilities. Why S curve? Isn't this something like a parabola? If I just twist it, parabola is like this, right? If I just change it, will this not be expressed in mathematical concepts, mathematical equation? It will be, right? So all the statisticians in the world, all the data scientists, machine learners, machine learning engineers, research scientists, they looked at all these curves. You and me, we don't have to. They looked at all the possibilities in the world and they said this S-shaped curve is the only way that we can solve this problem. Imagine we looked at the curve, right? We looked at how we interpret it. So imagine this is your keyword at 2. Okay. And this is at 3, 4. Now at 4, if you try to plot it on your curve, will it not give 3 values? Will it not give you 3 values here? Correct? This is spam. This is not spam. So for one input, you're getting 3 output. You're saying there is a possibility of this being not spam, and this is the possibility of being spam. This is the possibility of being spam. Only in one input. Will that solve our problem? No, right? For each observation, I need to tell whether it is spam or not spam. For each email, I cannot say that, there is this possibility, and this possibility. Then what is the use of machine learning? Here also, you'll get 2 points. Correct? So the idea was all these people, all these research scientists, they looked at everything and they found S curve to be the best. S curve to be the best, which could help us solve this problem. Or S-shaped. And could easily be converted to mathematical explanation. Okay. Cool. All right. So now you know why. Okay. And you know how. we are fitting a S shape, 0 to 1 probabilities. Now, I need to take you through one really important concept inside this for you to have further understanding in the logistic regression, okay, which is called odds, okay, and how it is different from probability. Okay, this is a good concept. Now, the idea is, let's say you have 5 red balls, okay, and you have 3, everyone from the non maths and non-tech background. We are revising a concept. I'll take you from the basic to explain you this odds concept, which is not really easy to understand. Okay, so pay 100% attention here, everyone. Okay, this is a really good concept and really a base concept for you to understand logistic regression. Okay, now when we used to understand our probabilities, correct? So probability was what? The definition of probability was number of events when it was successful, when success you have, okay, based on what you have, over total number of events. Correct? This was the definition. Now you have to give me an answer. Out of this, you have to tell me what is the probability of picking a red ball. Look at this. This is the definition. 5 by 8. Correct? 5 by 8. How did we reach to 5? This is the formula for probability, number of events when success. So you'll be successful when one of these balls are in your hand, which is one of the 5. So you can be successful out of 5 in 5 events, correct? Out of total number of events. Total is what? 5 here and 3 here. So 5 plus 3, 8. This is the probability, correct? Now, odds. Odds is slightly different. Okay. What is odds? Odds tells you likelihood, the likelihood of success with respect to failure. Okay. This is the very crude and very simple definition of odds. It is the likelihood of success with respect to failure, not with respect to total events. Understanding? Okay. So in the same example, okay, if I say, what are the odds of picking a red ball? What are the So in this, there is another concept of favorable and unfavorable. I am just saying whatever I'm saying, it is favorable. Okay. What are the odds of picking a red ball? 5 by 3. Why? Imagine this to be success, number of success events, and number of failure events. This is your odds. Meaning, in this case, it would be 5 and you could fail in 3 of them when you pick one of the yellow balls. So this is your odds. Okay. So what you're doing is you're doing 8. 8 is total events. You only need to count failures. You're saying how likely am I to be successful compared to my failure, not probability of me becoming successful. There's a very slight difference, but once you go through this concept now, once again, revise it, you'll be able to understand it. Okay. It's slightly mathematical. I've tried to, simplify it to the core of it. Okay. Perfect. Cool. Now you know what is odds and what is probability. To concrete this concept further, let us understand a few more examples. This, okay, is fine. We've already looked at it. Where is logs? Okay. So this is one concept. Let's say this guy went for fishing 5 times in a week. He caught a fish on 2 times and he failed 3 times. Okay. So the probability is what? Probability is chances where he was successful over total chances. Okay. So he was successful in catching the fish twice. Out of how many times did he go? 5 times. So 2 by 5 is the probability. But odds, what is the odds? Odds is number of times when he was successful to catch the fish and number of times when he was not able to. He failed to catch a fish. Okay. So these are your odds. Another example. Ignore this log it and everything. Another example is so this is the predictions, okay, of a rainy day and a sunny day. Okay. Now the odds of catching a sunny day is green means yes, red means no. Okay. The odds of catching a sunny day is 2 by 3, 2 over 3. Okay. And the odds of catching a rainy day is 3 by 2. Red is yes, green is no. Okay. 3 by 2. There was rain on 3 times and it didn't rain on 2 days. So 3 by 2. Now you could also take a ratio of these. 2 by 3 divided by, this is what they are doing here. Okay. You could also take a ratio of this. Now this ratio is called odds ratio. This ratio is called odds ratio. Okay. Let's do one thing. Why am I teaching you this odds concept? What is the reason behind this? The reason behind this is that whenever you are doing logistic regression, when we were doing here, okay, we understood the curve has to be fit in an S shape. But at the end of the day, I am comparing my spam with not spam, right? I need to know an email is spam, how likely it is to be a spam and how likely it is not a spam. They have to compete against each other, not out of how many I have spam. For one email, I have only 2 decisions to make, spam or not spam. So I have to compare these two. I need to compare the odds. I need to compare what is the likelihood. The keyword is likelihood of an email being a spam and a not spam. That doesn't come from probability. It comes from odds. Okay. That's why it is very similar to probability. So it is easy to get confused, but that's the minute difference. I am deciding for an email or a 0-1, okay, win or a loss, fraud or not fraud, whatever example you take, I am competing with the other one. So I need to know my chances of success compared to my chances of failure. In other words, my chances or my likelihood of catching a fraud person versus my chances or likelihood of not catching a fraud person. Understood? Okay. Keyword is likelihood. So it's not plain probability, it is odds. Perfect. Now you know this. Now you already know this. Let's move into the logistic regression further down. Okay. Now, look at this very clearly. Okay. Can I say odds is equal to probability over 1 minus probability? Can I say that? Let me give you an example. Why I can say that. So in the red marble and the yellow marble example that I gave you, okay, over there, the probability was what? Probability of catching a red ball was 5 out of 8. Correct? And let me put this in this way. Red, it was catching a red ball was 5 out of 8. Okay. And catching a yellow ball was what? 3 by 8. Everyone with me. And what was the odds? Odds was 5 by 3. Now you understand where I'm going. Can't you say 5 by 8 over 3 by 8? This 8 and 8 will cancel. Will it not left? You will have 5 by 3, which is same as odds. Probability of getting a red ball over probability of not getting a red ball. Isn't that odds? If you're successful, that is probability. And over not or being failure, can I not say failure is probability of not being successful? Correct? Okay. So now let's derive a few things. Okay. This will be very, just follow me. We are not doing really high rocket maths. It's very simple. Okay. Two things I need my non-tech guys and also people from tech background and mathematics background to remember or revise this. When you have to take a log of A by B, what is this? This is nothing but log of A minus log of B. Correct? If you have not studied this, this is the property. Okay. This is the property of logarithm. I have not derived this. It is already there. Okay. Now we know odds is equals to probability over 1 minus probability. This is your first step. Second step, take log on both sides. What will happen? This will become log of odds is equals to log of P over 1 minus P. Correct? Okay. And I'll tell you what is the equation of sigmoid function. Sigmoid function is nothing but 1 over 1 minus e to the power minus x. This is your sigmoid function. Okay. Why I'm telling you this is because in linear regression, our equation was y is equals to mx plus c. Correct? In logistic regression, it is this. 1 y is equals to 1 over 1 minus e to the power minus x. Okay. That's why we are going to reach from here. From here, what we learned, odds to probability to this equation. How do we reach there? We're going to derive it. And trust me, this is the line that we'll be working with. This is the line that we have been working till now in linear regression. Okay. Now we already know it is an S shape. Don't take my word for it. It is the S shape that in logistic regression we have to use. And how do I say it is going to follow this. It is going to be this. How do I say this? Let's prove it. Okay. We'll go into mathematical derivation also, but I want to show you this as well. Okay. This is Desmos. It's nothing but a chart, right? What happens is if I put an expression here, which is y is equals to 1 divided by e to the power minus x. Okay. Don't you see this is an S shape? This is the equation, guys. Y is equals to this. Okay. If I zoom in, whatever we have studied till now, it cuts exactly at 0.5 and it does not go, whatever the value of x is, it does not overlap 1. Basically, it is asymptotic to 1. And on the negative side, it is asymptotic to 0. What have we plotted here? We've plotted this. Okay. This is the best curve for us to say whether it is 0 or 1. Correct? S shape. And this is the equation. I'm proving it to you right now, showing you visually at least. Are you able to understand that this is the equation for us to get this kind of shape, an S shape? No matter, is it going above 1? No, right? It is not. Is it going below 0? No. Correct? Okay. This, let's say y is equals to e to the power x. Okay. This is the graph and y is equals to log of x. This blue line is log of x. Okay. And this is your e to the power. Exponential, opposite of exponential is logarithm. Okay. So this is the graph of logarithm and this is the graph of exponential. And I'll tell you why we need this. Okay. I'll show you. Here is why we need it. So for example, y logs. Okay. Let's say you have 3 to the power x is equals to 9. Okay. Can you not write it 3 to the power of x is equals to 3 to the power 2? This is 9. 3 to the power 2 is 9, right? So with this, can't you say x is equals to 2? Correct? That's why for these, we take exponentials. This is nothing but this is exponential. Okay. And sometimes when these, things are really complicated, we take logs because log is nothing but ulta of exponential. Okay. It is exactly the opposite of exponential. Okay. Now, homework. I need you to look at these two things. Okay. Homework 1, adjusted R square. In linear regression, we studied R square. We need to look at adjusted R square. Okay. Then there is something called as VIF. I cannot cover everything. Okay. I'll try to cover things that are important from the interview side and for you to understand. And I'm going to give you some homework that is going to improve your understanding, overall understanding. Okay. You need to tell me what is VIF. It is variance inflation factor. Inflation factor. Okay. And I'll tell you where you will see this. We looked at multicollinearity. You'll find it there. Okay. This will enhance your understanding of multicollinearity. Okay. And the third thing is log and exponentials. functions. Just look at their equation, just look at their graph, a few properties, graphs and properties. That's it. If you are able to do this, trust me guys, logistic regression is going to be a cakewalk. Okay. And first two are for you for linear regression. Third, if you do, with me, logistic regression is going to be a cakewalk. Not only the explanation, the intuition, also the hands-on. Okay. These two are really base. Linear regression for regression and logistic regression for classification. Okay. Okay. So cool. Now what is adjusted R square? Let me take this up. First one, what is adjusted R square? So now R square we understood, right? It helps us to tell how better is our model with respect to the average line basis of the errors. And more the value of R, the R square, better the model is. The idea is to be around 1. So now, guys, they notice that there is a slight problem with R square. So adjusted R square came because R square will increase with increase in number of independent features. Why was that the case? So let me give you an example. So imagine you are trying to predict your exam score. Okay. You're trying to predict your exam score. Imagine you're going into the exam. Okay. And you want to predict your marks that you'll score out of 100 basis the number of hours that you have studied. Okay. So the R value, so I'm writing the problem here, predict the exam marks based on number of hours studied. Okay. So you want to predict your marks based on, or you know, for a subset of students, you want to predict their marks based on exam score based on the number of hours that they have studied. Okay. Let's say you get an R square equal to 0.8. Okay. Meaning that 80% of you know, the marks can be predicted. It is, the model is better, 80% better, and you know, they can be predicted based on your marks, the number of hours studied. Now imagine I give you a feature, I give you their favorite color along with number of hours studied. I give you the favorite color of a student, and I tell you that, you know, now go and predict your this thing, favorite color of a student, your marks. Now R square will definitely increase. R square will increase. But does this feature have any importance? Will it tell you the favorite color of a student and will predict its his or her performance in the exam? No, right? No. So to penalize the R square, so R square always increases with the number of features that you pass in, okay, to your model. To give some sort of penalty to R square, they came up with something called as adjusted R square. So adjusted R square penalizes your R square. Internally, it is the same thing. It calculates the same thing. There is some relationship between adjusted R square and R square that is up to you to figure out. But in that formula, you will notice that it penalizes your R square. It penalizes R square based on predictors. Okay. It also has based on number of predictors. It gives more importance to the ones where the feature is actually important for your model. So in the above case here, adjusted while the R square will increase, okay, but adjusted R square will most likely be same or it will reduce. Okay, that's the concept of adjusted R square. Now, what is the next one? Okay, VIF. So I also told you that it is coming in multicollinearity. Okay, I give you a hint. So let's look at the other example, VIF. Now, VIF is variance inflation factor. It is used to detect the multicollinearity in your data set.
Okay. The concept is very simple. The concept is very simple. Imagine you have
Four features, feature 1, feature 2, okay, feature 3, and so on, and feature 4. These are your independent features. Independent features. What VIF will do while
doing that linear regression or finding a multicollinearity,
it will internally try to plot feature 1 with feature 2. It will try to do linear regression between feature 1 and feature 2. Then feature 3 with feature, or it will do the same thing, but just to maintain the consistency, it will do it like this. It will do with feature 1 with feature 4. And we'll try to see if there is a linear relationship or no. If there is, then the VIF value will become very high. It will become very high if there is a linearity. Okay. It will become really high. And you will have to, whenever you're running your linear regression, you have to remove the feature with really high VIF. Okay. Remove it and run the VIF again. Run the linear regression again. If you still see some relationship, some feature having a VIF really high, remove it, do it again. That way, you'll be able to
eradicate your multicollinearity. Okay, all of you with me on both these concepts. So this you don't have to do. It will automatically calculate VIF. It will automatically calculate VIF. There's these
things in the linear regression, but you need to know how to implement it, how to even think about VIF. Okay, so that was the idea. Okay, cool. So the other thing is, what was the other thing? Log and these functions. Exponential graph. Okay, we'll go to the images. This is your exponential graph, and there should also be exponential and log. Yeah, this one should be fine. Yes. Okay, so this one is a to the power x, which is like this, and this is log with base a to x. This is how the graph looks like. Okay, two things that you have to remember for the log is, in this graph, log 1 is equal to 0. Okay, when log 1 is equal to 0, and log of 0 is minus infinity. Okay, and what will this value be? And this is the value of e to the power x, or a to the power x here. E to the power x is also similar. Okay, cool. Okay, so I will remove this 3 we've already covered. Now let's go into logistic regression in deep detail. Now, the idea is that we had this graph, correct? We had this graph which had a line like this, and we had a few males here, okay, which were spam. And then there were a few here which are not spam. Okay, cool. So there were a few here. And here was your keywords. Keywords, high security keywords. We looked at them, lottery, prize, and all those. Okay. So this I will categorize as 1. This I will categorize as 0. So we looked at this. Now, how did we come to this? Okay. The idea, we talked about log of odds, correct? We also said this is 0.5 here, somewhere in between. So the idea is that we looked at, now this is one value and this is 0. Originally, I also told you that we have to be slightly different from probability. We have to move towards odds because we have to compare whether it is a spam or a not spam. Okay. Out of not the total, we have to consider the odds. So we had looked at this formula that odds is equal to probability over 1 minus probability. Okay. So if we take the log on both the sides, this will become log of odds and this will become log of p over 1 minus p. Okay. This is what it is. Now, what I also told you, the property of log that you need to remember is log of a divided by b is equals to log of a minus log of b. Okay, this is one property. Now, what happens is, let me pick this here again. So now we have this. Okay, what if? Let's look at two cases. What if? Case one, probability is 0. Okay, if the probability is 0, will it not be this, that I will be, my log of odds will become what? Log of 0 over 1 minus 0. Correct? I'm putting just the value of p here. Okay. So what will this become? This will become log of 0 minus, now we are taking advantage of this property and we are going to say log of 1. Okay. And just now from the graph, what did we see? What did we see from the graph? Log 1 is what? Log 1 is 0. And what is log 0? It is minus infinity. Meaning it will become what? Minus infinity. So this point, when I'm saying it is 0, this is log of odds, right? So if it is 0, can I say, let me put it here. Okay. So we're looking at this case 1. Let's also do the case 2. Let's also do case 2. Case 2. When probability is equal to 1. Now in the same formula, log of odds, I'm writing it again, would be what? It is p over 1 minus p, and p's value is 0. Oh, sorry, 1 here in this case, in case 2. Then it will become what? This is log of this. Then this will become log of 1 over 0. Correct? This will in turn become log of 1 minus log of 0. Look, with this property, we are changing log 1 by 0 to log 1 minus log 0. So log 1 is what? Log 1 is 0, and minus of, and what is this log 0? It is minus infinity. So minus is plus infinity. Okay. So what is happening is, I'll tell you geometrically how you have to intuitively understand this. You have to intuitively understand this with this concept. Let me paste it here. Okay. So this graph, imagine it was here. We were here. between 1 to 0. Okay, we have looked at 1 to 0. And now will these values which were at 1 with the concept that we proved here, when it is 0, it will go here. These ones will go to minus infinity. Imagine I have this with me. Okay, here it is minus infinity, here it is plus infinity. Okay, now all my green not spam ones will be somewhere in the infinity, minus infinity. Okay, and all our positive ones which are 1 will be somewhere in plus positive infinity, at positive infinity. Meaning now this line, this S curve line is somewhat like this. Can I say that or can I not? It is somewhere like this. Why? How did we reach here? How did we reach here? We know this is log of odds. Okay, this is log of odds, this axis. Okay, now what we are trying to do is we are trying to put the values of probability. Now if we do a probability, we know that our 0, whatever males that we have as not spam, which is 0, okay, will go to minus infinity, and the ones that we have at 1, which is spam here, will go to positive infinity. Why? How will they go? What I have done, I've just replaced the values in the formula. Okay, meaning that we can move this graph, from 0 to 1 to a minus infinity to plus infinity problem using log of odds. We want 0 and 1. This is the outcome that we want between this. But originally it is like this. So these values, so what we have done, we have just expanded our y. We have not done anything to your x. So here there were keywords. Here also there are keywords. More the keywords, it is going to be spam. Less the keywords, the likelihood is that it is not going to be spam. Okay. So we have just expanded this y. We have just expanded the y. We have not expanded your x-axis. Okay. So basically, the question that I was trying to ask, or I was expecting, that logistic regression has a word regression in it, but it is a classification algorithm. Correct? It is a classification algorithm. Then why regression? It is because of this. Okay. So what happens is, since logistic regression has all the essence, all the mathematical fundamentals of linear regression, it is called logistic regression. So nothing but you have the data like this from minus infinity to plus infinity. Okay. There might be different values for these spam and not spam. But since you want this minus infinity to plus infinity, you want to squash the y value between 0 to 1. Squash as in you want to contract this infinite y axis between 0 and 1, because that is meaningful for your problem. Okay. So all the concepts of fitting the line and everything is very similar, and also the mathematical concepts are very similar to linear regression and logistic regression. That is why it is called, in the name it is logistic regression, but internally what it does, it is a classification algorithm. Okay. The underlying concepts are like linear regression, but the way we want to solve it is with S curve. We cannot solve it with a linear line. But internally, if you look at it, it is a linear line. But we are somehow changing this linear line to an S curve using some function. And that function is called sigmoid. Sigmoid. Sigmoid function. Okay. And it is generally said that now your y cap is nothing but sigmoid of z. Z is nothing but your value or your line equation. This is nothing but sigmoid. In linear regression, what was it? In linear regression, your y cap was w0 plus w1 x1. Let me write it again. So in linear regression, your y cap was what? w0 plus w1 x1 plus w2 x2. And depending on how many variables you have, it was wn xn. Correct? But in logistic regression, this is your equation. And this z is nothing but, it is some combination of linear line only. Some combination of this linear line. Everyone with me. What you're doing, what you're using this sigmoid function is to squash the output between 0 to 1. This function is just doing that. So basically, you're getting some line in logistic regression. Okay, let's compare linear regression and logistic regression. In linear regression, we were fitting a line. We were looking at the errors and we were finding the best error. That's your best line. Okay. That is what you are doing in linear regression. Now in logistic regression, what you're doing is you're essentially also doing the same concept, but then you are wrapping that everything inside a sigmoid function. Sigmoid function, which helps you to get the output between 0 to 1. Okay. And sigmoid function works on what? Log of odds. How you can do that? You can do that based on log of odds. Okay. Now with an example. So let me take the same example of churn. Churn example. Now imagine you have this. You are trying to predict which customers are going to churn. Okay. And you have this. You have discounts. You have discounts in your x-axis and you have number of calls that the customer had to make to customer support. Okay. So what would you see? The number of people who have lesser discounts and have more problems, meaning they're reaching out to customer support, will be somewhere like this, right? And the people who do not call that much to customer support for their problems and also have high discounts will be somewhere here. Correct? Let me put in some more values, some more data points. This is how in real world you'll get the data, right? This is how you will get the data, right? Your idea is to find a line that separates this. This is your logistic regression. Idea of logistic regression is to club all the people who are going to churn, all the red dots separately and all the yellow ones separately. Is this line not doing that perfectly? This is what logistic regression is, right? It is trying to fit a line that perfectly classifies your examples or your data sets between yes or a no, between red or a yellow. Okay. Will this line tell me, will this line not fit or will this line not tell you perfectly? Perfect. Now, one very stark and a very powerful explanation that will clear all your concepts in just one example, in this one visualization. Okay. Which is what is the concept of linear regression? What is linear regression going to do here? Linear regression will try to fit a line like this, right? Because over there, the motive is to reduce the error. to fit a line that reduces the error, not separate them. Correct? It wants to fit a line so that it passes through almost all the data points if it can. If it cannot, then the error should be less. Everyone with me? Now you understand the difference between regression and classification also. So logically thinking, people who have really high problems with the platform and who are not given really huge discounts, they are more likely to switch, right? So those are your red dots. And the people which are your yellow crosses or the yellow people, they are the ones who are having least number of problems with the platform. They don't have to reach out to customer care again and again, and they are being given really good discounts, really high discounts. So they'll be happy, right? They will not churn. So here, red one, churn, probability is high, and here, not churn. Let me write it that way, not churn. Okay. The idea of logistic regression is to separate the red and the yellow points completely out. And for the linear regression, the idea is to fit a line so that the errors from all the data set is really less. There is some linear relationship between number of calls to support customer care and discounts. Okay, cool, perfect, guys. So now this out of the way, let us also do some derivation. Let us do some derivation. I will now mathematically prove it. I have proved it visually and geometrically that, this is this, and I've also given you an example how it works. We are just, solving something really under the layer of logistic regression. We are going into real details that why it is called regression. One, even though it is classification, how does it fit my data? Okay. And what does sigmoid do? Sigmoid is nothing but it is just a wrapper on this line. It is just a function on this line, which will now help me to say whether it is 0 or 1. It will give me probability whether it is between 0 or 1. Okay, that's the only thing. Now with derivation, I am going to prove that. Okay, so now this will not take much time, guys. Odds, we already know that this is this. Now taking log on both the sides. This is first step. This is second step. Taking log on both sides. It's log of odds. Log of p over 1 minus p. Okay. Then we go into, now with the example that I showed you that, this curve, this S curve can be converted to a problem which is from plus infinity to minus infinity using this, right? Using log of odds. So what I can say is, in other words, if I, instead of this, I put the equation of line here, which is W naught plus W1x is equals to log of P1 minus P. You understood why I put this value, equation of line? Just now we saw it visually, right? Now the other property. This is the third. Okay, this is coming from here. Proved already. And then the fourth line is property. Now this is for all the non-tech people and people who have not looked at exponential. Okay. Property is that whenever you have to get rid of log, you take an exponential. So the property is log of to the base a for log of x. Let me put n here. Log of some number And if its value is some feature, this can also be written as n is equals to a to the power x. I am not doing anything here. It is the property. I'm just putting it here so that you can quickly revise, and all for my non-tech people as well. Okay. So we are going to do the same thing here with this. We are going to do the same thing here. So this will become what? E to the power W0 plus W1x is equals to probability 1 minus probability. Okay. And now fifth step is that now I will just solve this problem. I will take this here. Okay. Chain rule. I will say something like this. Just be with me, guys. It is going to be multiplied by 1 minus p. Okay. And now I'm going to take this e to the power w naught plus w1x inside. It is going to become e to the power w naught plus w1x minus p times e to the power w naught plus w1x1 is equals to p. Now I'm going to take this p here again. Okay. It is going to become e to the power w naught plus w1x is equals to p plus this minus will become plus there, plus p times p multiplied by e w naught plus w1 x1. And now if I take common p out of this, seventh step is e to the power w naught plus w1x is equals to p 1 plus. Now anyone who can see where I'm going with this? The last step is if I bring this here, this side, what will it become? It will become e w naught plus w1x over 1 plus e to the power w naught plus w1x is equals to p. Have you seen this equation somewhere? Have you seen this equation somewhere? Since you have not seen it, what you can do is you can divide. This is an optional, step. This is 8, so we'll go into ninth step. Ninth step is you divide both of these with e to the power this term. Okay, so this will become e to the power w naught plus w1 x1 divided by e to the power w naught plus x1. Here in denominator, it will become 1 plus e to the power w naught plus w1 x1. This entire thing divided by e to the power plus x1. In a nutshell, I will not go into the maths. In a nutshell, this will become this and this will cancel out. Okay. This and this will also cancel out, but this will come here. So it will become 1 over 1 plus e to the power minus of w naught plus w1 x1. And if you say w naught plus w1 x1 is equals to y cap, this is nothing but 1 over 1 plus e to the power minus y cap. What is this? This is sigmoid. Didn't we talk about this? This is the equation of sigmoid. Okay. This derivation, no one is going to ask you. Okay. No one is going to ask you, but I wanted to show this to clarify that mathematically this is possible. This, can I not say that this is nothing but some verification, some function of your sigmoid, which is given on y cap. Okay. So sigmoid will give you the probability. What did we have here? We had probability here, right? So it will give you the probability here when you're trying to look at all the values. It will convert this linear line to a value where it can be looked at as a probability. That how much probability it is to go to spam, how much probability it is to go to not spam. No one is going to ask you this derivation, but it is very important to know, at least from the understanding, that how did people go from this S curve, or started with linear line, go to an S curve. Okay, perfect. All right, guys. So I think we have covered this. Now let me see what I wanted to. Okay, we have already talked about the balanced data and the imbalanced data. Imbalanced data. Okay, we have already looked at the fraud problem. Out of 100 applications, 95 of them are genuine and 5% of them are fraud. Now, if you are a very smart person, okay, why you will think that I'm getting all the applications. If I make a model, or if I tell that whatever application you're getting, just predict that it is what? Genuine. If you just make this, if you train your model just to don't pass anything, just constantly say that it is genuine. Whatever loan, that application that you're getting is genuine. Then how accurate will your model be? You have 100 emails, out of which 95 of them are genuine, 5 of them are fraud. So this I will say not fraud. This I will say fraud. And if your prediction is, your y cap is 100 of them are not fraud. For all of it, you will say that this is your prediction. What is the accuracy? Accuracy is 95%. This is called dumb model. Anyone can make this dumb model. No brain. But is this 95% right? Even though it looks like 95%, it looks like a really huge number. Is it doing what we need to do? If tell me bank processes the loan for these 5 people, you know how many people have gone out of India, right? They have fraud. They are frauds. How much money can they take away with them? All these 5 frauds or 4 frauds or whatever these people are. If you end up giving loan to them, they will never repay. They will run away with bank's money and it is lost to the bank, right? Even though your model is 95% accurate. Is your mind blown? And you are simply saying you have created a very stupid model that whatever application you're giving to me, just say, yeah, process the loan for this guy. It is always saying not fraud and process the loan. That's not right. So the important thing for here, what is important here? The important thing is that we do not process loan for even a single fraud person or a fraud application. That's how that is what the banks want, right? That is the ultimate goal of the bank. So here with this example, you know that accuracy is not the right measure for classification problems. Or let me put this this is going to, you know, something that people generally ask in their interviews, that why accuracy is not used. Looking at alone accuracy is not the right measure for classification problems. Everyone with me? Even a dumb model can tell you that, you know, with 95% accuracy, you're not building any model there. You just put one line that whatever in the code, your code will look like this. Just say or predict there's a constant value there which says not fraud. Still, it is having 95% of accuracy. This is why data scientists, machine learning engineers, AI engineers like you are paid really high, because anyone can make that 95% accurate model. But you are the one who need to go in detail and see that what is the ultimate goal of the problem. The goal is, I shouldn't, okay, I can process for all 95 of them, but more important for me is I shouldn't be processing the loan for these 5 people, especially. Okay, I can reject 7 of them. But out of all these 100, 2 could be people who were genuine, but I still ended up predicting fraud for them. But I need to make sure all of these, my 7 applications that I'm rejecting, they should be at least closer to fraud. They should have all these 5 loan applications, which are absolutely fraud. There is some collateral damage by rejecting loan for another 2 people or 3 people, which might or are at a risk of fraud based on the probability. Okay. So that is why accuracy is not the alone looking at accuracy is not the right measure for your classification problems. Okay. Especially in imbalanced data set, even in balanced data set, never look at accuracy alone. In classification, we have something called as confusion matrix. Confusion matrix. Okay. We have something called as confusion matrix. Why the name? Because it confuses a lot of people. It confuses a lot of people. That's why the the name is confusion matrix. So you need to be extra careful when you're doing classification. Okay. So we know that the outputs can be only 0 and a 1, right? The outputs can only be 0 and a 1. So what will you have? You will have this. Okay. You will have this. So here imagine, okay. So imagine this is your Y cap, meaning predicted. Okay. And here is your Y, meaning actuals. Okay. Now you could be predicting, I'm going back again to the spam and not spam because it is easy to understand that. And we've been talking about that example really well. So this is not spam. Okay. You have predicted it is not spam. All the values on the columns are your predicted, and you have predicted it is a spam. Let me do it this way. And the actuals are, it is actually a spam mail. Okay. It is actually a spam mail, not spam. Let me put that in green. And in actual, it is not a spam. These are the 4 instances that can happen that you have predicted. What does this block say? This is 1, 2, 3. What else? 4. Okay. What does 1 tell us? 1 tells us 1 is y cap is, let me put this as 0, 0. Okay. Prediction is not spam. We already know. I'm not marking it here. Okay. Not spam is 0. Spam is 1. So here it is 0. Your y predicted is 0. And y cap is your y 0. So this is what? This is correct, right? You have correctly predicted that it is not spam, and in reality also, in actual also, it is not spam. I'm talking about this one. Okay. Let's go to the second number in this box. What is this? This is, you have predicted it is a spam, meaning y cap is equals to 1. And what is your y actual? Y actual is 0. This is wrong, right? This is wrong, right? You have predicted that it is a spam, but in reality, it is not a spam. This is the reality here. It says that it is not spam, but you are saying that it is spam. Okay. Now let's look at the third one. Third one is, what have you predicted? Prediction is not spam. In reality, what it is? In reality, it is spam 1. Y is equals to 1. Y cap represents, or this hat or a cap, okay, represents your predictions. So you have predicted 0, which is not spam, okay, and in reality it is spam. So this is also wrong, right? This is also wrong. You have missed. And the last one, which is the fourth one, 4 here, you have predicted it to be a spam, meaning you have predicted it to be 1. And in reality, it is 1. So y is equals to 1. So this is correct. So these two are wrong, but these are right. Correct? So you need to get the maximum value here. 1 and 4 should be high because they are correct. But 2 and 3, the numbers 2 and 3 here should be low as much as possible because they are your errors. Correct? I am just uncomplicating or unconfusing this confusion matrix with you. So just go with me step by step. Okay? Because if you come back the next week or even the next day, you will get confused which one is true positive, which one is true negative. What is that? What is not that? So I'm just, everyone in the industry confuses on this a lot. That is why the name is confusion matrix. Okay. So just stay with me. I am making it unconfusion matrix for you. Okay. Now, if you look at it, logically, let me copy this to save time. Okay. So the idea is, if I remove this, the idea is all of these, they have two values. They have two values here. I want 100% attendance here. If you look at this, okay, if you understand what I'm trying to explain, you will never forget in your life what is confusion matrix. And trust me, guys, this confusion matrix is really important and is one of the best pet questions of your interviewers. Everyone asks this. everyone, in one way or the other, everyone asks this question. Okay. Now you have to fill these two blanks here. What are these two blanks? Okay. One tells you what you have predicted. Okay. The other tells you whether you are right or wrong. You are true or false. Okay. So here, let's say not spam is what? Is negative, right? Let's say this is negative. And spam is positive because we are trying to get which is spam. So for us, it is a 1. So it is going to be positive for us. Okay. It is going to be positive for us. Now, what you have to tell me is, you have to tell me what value will come here. We'll first fill the second blank. This is spam. What have you predicted? This is negative, right? You have predicted negative. And this is not spam. And in reality also, this is not spam. So is this true or a false? T, right? So we are doing true here. What should I fill here? In this second blank. What is your prediction? Spam. Spam is positive or a negative? It's a positive. And you have predicted it is spam. But in reality, it is not spam. So this is true or false? F, right? Here again, here. What should I put here? You have predicted what? Positive or a negative? You have predicted what? Positive. And this is, you have predicted spam. It is also spam. This is true. And what will this come? This is, you have predicted negative. You have predicted not spam and it is spam. So this is what? False. Congratulations, guys. You have completed logically. You have completed or filled confusion matrix. And trust me, I'm coming from the industry. I take interviews, and the amount of people who get confused between TN, FP, FN, TP, where it should be, where it should not be. The amount of people who fail into this and are not able to answer this are startling very high. This is such a basic, but this is where you create the impression. If you're not able to answer this, interviewer will be like, it doesn't know anything. This is just basic. Okay. So now these are called your type 1 errors. Type 1 errors. And these ones are your type 2 errors. And trust me, guys, even I get confused. Even I get confused. Okay. So this is the way that you can, instead of memorizing, logically you can understand. We'll talk about what are these two errors, type 1 and type 2. But now, can you tell me what is your ideal model? Ideal model based on the spam example only that I gave you, fraud example. Fraud example of 100 fraud or 100 applications. So based on this, what we have studied, okay, can we say that these two numbers have to be the maximum? Okay, this has to be not spam, this is not spam, and this is spam, this is spam, this is your Y cap, this is your actuals. Okay. So these two numbers have to be really high. So in ideal world, the ideal model, you had 95 of them which were not spam or not fraud. Let me in fact change this to fraud problem. This is fraud. Okay. And this is not fraud. How many of them were not fraud? 95, right? In reality also it is 95. And you would want to, your perfect model will also want to predict all 95 of them as not spam. So this will become 95, correct? And 5 of them were fraud. In reality, your perfect model or ideal model would want to predict all 5 of them correctly. And you would want to make these type 1 and type 2 errors 0. Correct? This will give you what? 100% accuracy because your errors are 0. This is the perfect model. The example of the fraud. What did we do? We say that we have 100 loan applications. Okay. And out of them, we know 95 of them are not fraud. We know, okay, they are not fraud. And 5 of them are fraud. We know this. So your job as a person who is working as a top level data scientist with some bank, let's say JP Morgan Chase or HDFC or Citibank, Axis, anyone, Mashreq Bank from Dubai and all, even in Swiss Bank, imagine, even Swiss banks, you are given the responsibility to make a model that is perfect. How will you make it? Your goal is that you should be able to predict all 95 of them correctly. You should make them as you should predict that they are not fraud for all 95 of them, and you should also be able to predict that these 5 are only the fraud. That is your perfect model will have 0 errors, because we have already seen that this false positive and false negative are type 1 and type 2 errors. There are some sort of errors. What type of errors? We'll get into it. So your idea is that these two values should be 0 and these two values should be absolutely correct. So your model should predict it is not fraud. And in reality, we know 95 of them are fraud, not fraud. In reality, in actual, we know 95 of the applications are not fraud. Your model should also say 95 not fraud for these 95 applications. So I'm putting a 95 here. Okay. Your prediction of fraud should be exactly the same where these are fraud. In reality, if it is a fraud, your model should also say it is a fraud. Okay. All right. So now what we have seen is we have seen the confusion matrix. We know how to fill the confusion matrix. We know what type 1 errors and type 2 errors are. It is nothing but some sort of incorrect, right? So they have a false in front of it. False positive is your type 1 errors. False negatives is your type 2 errors. And then we also looked at what is the ideal model, So this one would have 100% accuracy. Okay, 100% correct. Let me put it as accuracy also. And here the accuracy is also good. Why? Because your type 1 and type 2 errors are 0. Okay, so we are not looking at only accuracy alone. We are looking at the errors also. Okay, now formally what happens is there is something called as precision. Okay, so there is something called as precision. Okay, let me talk with an example. There are two cases in your spam and not spam. One is you receive a spam mail in your mailbox, in your inbox, meaning it wasn't classified as in spam, but it is a spam. And what is the other thing? The other thing could be that your, I hope this doesn't happen, but imagine if this would happen, how bad it would be. Your offer letter that came through an mail goes to spam. Tell me now, guys, which one is more dangerous here? This thing is harmless, right? This thing is harmless. You are receiving a spam mail in your inbox. It is there in your inbox, but action is not yet taken by you, right? But you interviewed somewhere and you got the job. The offer letter did not reach in your inbox ever. It was wrongly classified as a spam mail. So that is more dangerous to you, right? Now you're thinking that you are not placed, you did not receive any feedback, any offer letter from the company, but in fact you have already been shortlisted and given the offer letter. So this is dangerous, right? So this is dangerous. This is more dangerous. Now let's think about this. What is this? This is a false positive or a false negative? What is the first one? We are just making our understanding even more concrete with these examples. Okay. First is false positive. FP, correct. So remember we spoke about two fill in the blanks that we have to do whenever we are doing such things. So what did we predict? It is an actual spam, but what have you predicted? You have predicted not spam. You have predicted not spam. That is negative, right? You have predicted negative. And it is a spam mail, but it came in your inbox. That is false, right? Your prediction of negative is false. So this will be false negative. And this one, what is it? What have you predicted it to be? You have predicted it to be a spam, which is 1, 0 or 1. 1 is positive in our case. And that is also wrong, right? So all those who said it's false positive, do you understand why it is false negative and why the second one is false positive? So the first one is that you received a spam mail in your inbox. Okay. Imagine that you have a model which is responsible to pushing those emails which are not spam in your inbox, and the ones which are spam according to the model should go to the spam folder. But this one came to your inbox folder, meaning what has your model predicted? Your model has predicted it is not spam, meaning it predicted negative. Out of these two fill in the blanks, it predicted a negative clause for it, meaning it is not a spam. And that decision is false because it is actually a spam mail. So it is false negative. The other one, second example, is that your offer letter has gone to the spam folder. Rather than coming to your inbox, that would have been the right thing. It has gone to your spam folder. So meaning your model has predicted that it is spam. So you have predicted what? Positive class for it, spam. Okay. And that is false. That is incorrect. So it is false positive. And in this case, false positive is dangerous. Meaning here the idea is that false positive should be minimized. Correct? Correct or no? And true positive should be improved. In this, if you look at this, this value should be minimized and this value should be maximized. That is your precision. So precision formula is TP over TP plus FP. How precise are your predictions? How precise are your predictions? On the positive side, how many are you able to correctly say they are positive out of all the ones that you have predicted as to be positive? Okay, how precise is your output, your predictions? Then second is recall. Now for recall, I have another example. I have noted it down. Okay. So now you have to tell me this. You have again two cases. The idea is that you have to predict whether a person who's having cancer, you have to detect whether it is cancer or it is not a cancer. Okay. You have to, your model has to tell whether looking at the condition of the patient or looking at the graph, your images of probably chest x-ray or something like that, you have to say whether it is the person is having cancer or he or she is not having cancer. Okay, cool. So there could be two cases. A healthy person is considered as cancerous. We are talking about only the errors. Okay, there are others as well, but I want it to be very clear for you, which is this type 1 versus type 2 errors. Let me put it down here. Type 1 versus type 2. Okay, this is one situation. The other situation is what? A person is cancerous, but you are saying that he is healthy. A cancerous person is considered healthy. Now first tell me, which one is more dangerous? Two, right? A person who is healthy will be starting taking the medications, correct? There will be some side effects of the medications, but it is not life threatening. And in subsequent tests, it might there might be a possibility that it is detected that this person has become healthy. So they would claim that the medicines have worked, but initially it was like, the person was healthy itself. Imagine it or relate this with your COVID also. A healthy person was considered to be COVID positive or a COVID patient. That is more dangerous, or a COVID patient, in the test it comes out that he's healthy, he or she is healthy. Okay, related that way also. So more dangerous is this one. Now tell me, what is this and what is this? Which one is false positive and which one is false negative? What is the first one? Let's look at it. What have you considered? What have you predicted? You have predicted that a person is cancerous, meaning 1. Cancerous is 1, non-cancerous is 0. When your motive is to find which one is cancerous. Earlier in the earlier example, which one is spam? So what have you predicted? You have predicted a positive for this. You have predicted that the person is cancerous, which is false because obviously the person is healthy. Now, can you tell me what is the second one? Second one is false negative, meaning you have predicted it to be a healthy, non-cancerous person, meaning you have predicted negative for it. And that is false because in reality, the person is having cancer. So it is false negative. So here we saw false positive was dangerous. Here we see false negative is dangerous. So depending on condition to condition, things change. Okay. Depending on your data, depending on what is your motive, and depending on what is more dangerous to have, which type of error is kind of acceptable, not kind of acceptable, but is less dangerous to the other one. So here the motive is that you need to reduce F negative, correct? Here you need to reduce the F negative in this one. Okay. You need to say that it is less negative. So the formula of recall is TP over TP plus Fn. Okay. Here the motive is that we should improve our true positives, meaning the ones which are cancerous, we need to improve their prediction. We should also predict cancerous patients. Okay. You're recalling out of all the ones which are positive, you should be able to tell the ones which are positive correctly. And you should have less people who are false negative. Okay. True and false is based on whether it is right or wrong. So here, this one, these are the two blanks that you have to fill, right? Let me close this. In this confusion matrix, it is two blanks. First one is what you have predicted. Okay, positive is the case when what is your goal. So if you want to identify spam ones, that is positive. If you want to identify cancer patients, that is your positive. Okay. And the second is whether what you have predicted is right or wrong based on actual. We looked at these, right? We looked at these 1, 2, 3, 4. All the ones that are correct are having your true there in the first blank. All the ones which are wrong, predicted versus actuals, they are false. Okay. It's not easy to understand this concept, but trust me, if you are able to revise this, I guarantee you, you'll never forget. The way I have explained it here, it is very logical, and also with examples, you will never forget it, given you understand this. Otherwise, the other option is you can simply go and memorize that, what is TP, what is FP, what is TN, FN, all those things. Okay. I would recommend you think it logically, and as and when you keep doing this, it will become second nature to you. You'll do this like this. Don't have to think twice. Okay. So this is your metrics that we call. So we have looked at now what is accuracy. Let us also look at accuracy. What is accuracy? Accuracy is the ones which are true over total, right? So accuracy based on your confusion matrix can be TP plus TN, the ones which are true over total observations, and total observations are TP plus FP, TN plus FN. Okay. Accuracy is nothing but all the ones that you're correct with over total number of observations. You're correct on 1 and 3 or 1 and 4, depending on whatever you're doing. These two boxes. You are correct only here and here. let me take it from here. 1 and 4 is where you're correct out of total. Okay. So that is your accuracy. And there is this one thing called, which is F1 score. F1 score. This is nothing but a combination, because now I told you that somewhere you would prefer to have a higher precision, somewhere you would prefer to have a higher recall. Depending, so in the cancer problem, you want to have a better recall, but in your spam and not spam, you want to have a better precision. So F1 score combines both your PR precision and recall. Okay. And how it is related is your F1 score is nothing but twice the precision over precision plus recall. Okay. Which in other words, what was your precision? Your precision was TP plus FP. Okay. And what was your recall? Okay. Let's leave the maths. There's enough, I feel. It is nothing but it is twice of TP over twice of TP plus FP plus FN. This is your F1 score. You can either use this one, the bottom one, or the above one. Is one and the same thing. Okay. If you solve this, no, if you put the values of recall and precision here, you will get this only. It's one and the same thing. Perfect. Awesome, guys. Is everything clear now? Logically, everything should be clear now. Okay. Why we need to look at accuracy in regression? Why we cannot look at only accuracy in classification? Okay. We looked at all the examples. Let's move on to the hands-on part. Okay. Cool. All right. Now let's go on to your hands-on. Okay. So here I have this data, which I've already uploaded. It is the heart attack data. Okay. So we've been looking at this all along. So let me go ahead and first, do all these. Okay. So let me first import everything. Import what? Pandas as PD. Okay. I will also import Seaborn because I want to show one thing in Seaborn also. I hope you have covered that. And then there were some others also that we were looking at in linear regression. Idea is same, guys. Idea is same. This is as, okay. Get the data, understand the data. Okay. Then separate your target and train variables, target as well as your test as your train. Okay. Do the split, get your independent features and your dependent feature separately, or your target feature separately. Then do the split. After you do the split, train it. After you train it, predict it. After you predict it, evaluate it, whether it is correct or wrong. So here I am importing. Okay. Then let me go ahead and, at least for a few lectures, I will not add all these things that I want in one go in the first cell, like I like to do it. But here, what did we do? What do we have to do? We have to read in your data frame, which is, let me say this as CSV. What is the name? Part1.csv. Okay, and then we will also do a head of it. Oh, okay, so this is our data. Okay, now what is the data set? What have I told you? That once you get the data set, try to understand whatever you want to understand of the data set, so that at least from making the model side, it is not important, but when that's the difference between a great data scientist or a principal data scientist, a great machine learning engineer, AI engineer, data engineer, all those things. That's the difference between the one who is great and the one who is just getting the job done. Okay, get the data, try to understand, even if it is not in your comfort zone. Now this data set is basically the data set of the people who get heart attack. Okay, now this is your target variable. It has already been given. Okay, I'll explain a few of these. Okay, because most of it is from the biology side based on the test, but this is the age of the patient. Okay, this is the sex, male or a female. CP here tells whether it is chest pain, and it is of 4 types: 0, 1, 2, 3. I know I've looked at the data, so I'm telling you it is 4 types. So it is basically whenever you get a heart attack, you more less or likely it is that you will get a pain in your chest first. Some pains are angina related pains, atypical angina, typical angina. If you go into these terms, you'll get to know about it. But for our understanding, these are different types of chest pains. Some are related to heart attack, some are not. Some could be, for example, could be due to gas, some could be due to something X factor, some other reason apart from heart. Okay, imagine it that way. Then this T rest BPS is nothing but your resting blood pressure. Col is cholesterol. This is fasting sugar, blood sugar. Okay, this is another ECG test is done in the heart, resting how it is looking like. These are some other tests. Okay, old peak is when it is peaking, slope, and these are all technical terms from the medicine side, but at least the ones that you're able to understand, you'll be able to get to know that okay, these are some of the conditions that are noticed in the patient, what are and some of the values of the tests that we are seeing here. And the target variable is 1 when it is a heart attack, 0 when it is not a heart attack. Okay, now let us look at and describe the data. What are we going to do? We are going to Okay, let me first do this. It has 303 rows and 13 columns. Okay, so patient is 303. We have the data for 303 patients. Now we are going to do df.describe. We will also do info. Okay. And then, okay, so what does the describe tells me? It tells me all the ones which are 303, the count looks like all of them are having right values. Okay. And then the mean age, on an average, the patient age that we are getting is 54, which is likely, right? People as in when they get older, the risk of getting them a heart attack is more compared to someone who's young, correct? So this connects with you. Then there is some ratio that we're seeing. The mean average is this. We cannot make anything about this because this is 0 and 1. Okay, categorical feature. The only thing that we can understand from this is close to 25% of the people are 0. Okay, meaning if it is a female, it is 0. If it is male, it is 1. Okay. So more than 50% of the data is from males. Then chest pain, what is the, again, categorical value here? So we are seeing 25 percentile, 50, 75 is 0, 1, 2. Okay. It is very equally distributed. Then BP readings. Okay. So here on an average, the BP reading is 130, which is kind of in the normal range, right? And some people have an extraordinary high BP. It's really high. 130, 120 is considered to be normal. Cholesterol value. See, the person who is having this high cholesterol is nothing but, as in when you keep on eating oil, it, or fat, the wrong fat, it accumulates in your body. Okay. It obstructs the blood to flow from your veins, arteries and veins. Okay. That could lead to heart attack. So a general normal value is below 200, but we are seeing all the patients, at least 25% of them or more, are having value 211. So high cholesterol is related to heart attack, even without looking at anything, even without, predicting anything. It looks like, high cholesterol above normal value is related to heart attack. Okay. And similarly, you can look at the others. Cool. Now, info, we are saying that, okay, all are non-null and I'm getting one float value and I'm getting 12 integer values. Okay. And the data set is pretty small since it is this thing, only 300 rows. Okay. So let's go ahead. What can we do next? So I can show you the value counts, meaning how many of them are 0 and how many of them are 1 in my target column. In my target column, out of the 303 people, I have 165 of them have a heart attack and 138 of them are not having heart attack. 0 is not having heart attack. Okay. So people also like to visualize it. So let me do a count plot using Seaborn. X is nothing but my target variable. And the name of my target variable is this. My data is df and my palette would be, palette is nothing but a color scheme. Okay. That you want to choose. So there are many color schemes that you can choose. I'm sticking to the one that I have been using a lot. Okay. So what error are we seeing? Palette spelling. What is the spelling of the palette? Palette. Huh. What are we seeing here? Let me just check what is going wrong here. Data is equals to df only. The spelling is wrong here. Okay. So now you see, let me minimize this. Now you see you have plotted around 138 of them are 0 and close to 168 of them that we have seen this number, 165 of them are 1. Okay. So we have just plotted a simple plot here. Okay. Now what is the next step? What is the next step? Next step is to create your data frame or creating your X and Y separately. Okay. So how are we going to do that? Everyone understands this iLock, right? We have covered this. So all the features, all the columns except the last one is your independent feature and only the last one is your target variable. Correct? So let's try to see x dot head. Let me not take much space here. So you have all the columns except the last one. And in your y, you have only one column, which is your target. Okay. Once you have done this, what did we do in linear regression then? We did splitting of the data. Okay. Now, how did we split the data? From sklearn dot models dot model selection import. What did we import there? Train, test, split. Okay. And then what did we end up doing? We end up creating my x train, x test. Second value is that. Then the third value is y train. Then we have y test. And what do? We call this function, which is your train test split. And what all values does it take? It takes your x, it takes your y, and it takes your test size. I am going to keep it again as 20%. And the last thing that we looked at, random state. I'm going to say 1. Any number, if you want to repeat it, any number. Okay, let me run this. Now, once you have this, let us look at sx train dot shape. It is 242 and x test dot shape. You know what? Let me print this neatly. Give me a second, guys. X train shape is equals to this. These are f strings, right? I hope you know. We also looked at it last time. And I want to say y train. Here I will change it to y. Just for creating some separateness so that it is easy to understand within this class. I'm just printing this. So this will be my test. This will be my test. Test. Okay, let's run this. Okay, so 303, 20% goes to test. So 30 and 30 close to 61, 30.3 and 30.3 close to 61 goes to my test, and the remaining goes to my train. And I have chosen it to be 80-20 because my data set is pretty small here. Okay, it's only 300 patients data. Cool. Now, what do we do next? What do we do next? In linear regression, what did we do? Create the model. Absolutely. Model fitting. So next we will do what? We will fit the model or build the model. Okay. Now over there, what did we do? Over there, we imported from sklearn dot, what was it? Linear. It was linear models, right? Linear model. We imported there what? Linear regression. What are we doing here? We are doing logistic regression. So we will import logistic regression. Okay, cool. Now what are we going to do? Over there we created a model, which is model. Now I'm just to make it separate. I am creating a instance of that class, which is your logistic regression. Okay, so I am creating this instance of the class in log model so that you are able to understand it is a log model. So log model, and what will my log model do? Okay, let me first show this. Let me run this. Now here, earlier we were getting linear regression. Now we are getting logistic regression, right? So log model dot fit is what we have to do. And we have to do fit on what? We have to do fit on train period, correct? Perfect. So we will do fitting here. Then this is nothing but warnings, okay? Data conversion warning and everything. Now, what is the next step? Predicting with the model. And everything that you have learned, all the patterns, all the relationships that you have learned, which is log model. So using log model, what are you going to do? You are going to predict. And you are going to predict on what? You are going to predict on X test. And you will save all your predictions in Ypred. So now you have your predictions, you have your test. Let me show you. This is your prediction. Okay. Let me print a few values. Let me also print a few values from your actual data set, your test. It's nothing but 0, 1, 0, 0, 0. Here you are saying 0, 1. Is there some change? No. Looks like you're predict. No, is there no? Here it is 1. Last, third and second last are 0, 0. Here you are predicting this to be 1. Okay. But in reality, it is 0. So you see one error there. Okay. Now we know what we have. What we have the predictions and we also have the actual values. Okay. We need another 5 minutes and logistic regression is done. So now what did we study? After we predict the model, we have to evaluate the model, whether the performance is right or wrong. So in linear regression, we looked at the evaluation should be done using RMSE, MSE, R square, okay, mean absolute errors. But here, what have we studied? We have studied confusion matrix, correct? So we will import what? Confusion matrix. So from sklearn dot, let me do that here. sklearn dot metrics import. From what are we going to import? What is the name? Confusion matrix. Okay. Python is very intuitive. And now to show you something, but okay, let me show that later. Let me first complete this. We're already 2 minutes up. So, so here, let me print this and let me call this as confusion matrix equals to. What do we do? First value is what? Actuals, right? First value is actuals. And then second value is your predicted. Then we will print confusion matrix. This is your confusion matrix. Okay. Let me copy paste this. This is nothing but that that thing that we were talking about. This is your what? TP, TN. This is what? FN, FP. So you're getting those values here. Okay. Now, another way that I generally try to use is this. Okay. I try to use confusion matrix display. It takes in the confusion matrix itself so that it can print it properly. Okay. Let me put this and then it has what? Display labels. What is the, let me show you what I'm looking at. Whenever I am stuck, I look at sklearn confusion matrix with labels, and this is the first one that I'm opening. And I go to the documentation and there is more likely or no, there is an example. So let me copy this. Okay. Your predictions label is equal to CLF classes. I'm putting that here. I wanted to show you this. But ultimately what it does is it shows you this. I don't want to take up much time. The same thing that you're seeing there, it shows it in a pictorial manner. Okay. So that it is intuitive to understand. Okay. Let me delete this and there is another thing that you can do, which is metrics, which is your classification report. This classification report, and then it does what? It is nothing but is the same thing. Just printing it. Classification report. And you're passing in the same thing there. First value is actuals, then second value is predicted. And you get all the things: precision, recall, F1, support is another thing, but accuracy, weighted average, macro average. This is what you're getting, right? All the things that we looked at today are everything here. Okay. So this is your logistic regression. Okay.
Just a quick info, guys. Intellipaat offers an executive postgraduate certification in AI and machine learning in collaboration with iHub, IIT Roorkee, and Microsoft. This comprehensive course is designed to make you an expert in AI and ML in just 11 months by working on over 50 real-time projects and industry case studies. With this course, we have already helped thousands of professional and successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to new height. So visit the course page link given below in the description and take a first step towards career growth in the field of AI and ML.
Okay. So here, now we have looked at all your precisions, all your recalls. We have looked at the evaluation metrics, but there is one more thing that I want to talk to you about. Okay. So I need you to understand this TPR and FPR. Okay. Can anyone guess what is this? Can anyone guess what is this? This is your true positive rate, and this is your false positive rate. The rate at which you are having true positives and the rate at which you are having false positives. Okay. The idea is that if you plot here, if you have TPR in your Y and FPR in your X, so false positive rate is you want it to be very less. The idea is you want to reduce this, right? And the idea is you want to improve your true positive rate. Correct? Everyone with me? Come on, guys. Everyone with me. You want to reduce your errors. In this case, it is false positive rate, and you want to improve your positive predictions, which is your true positive. Now, what happens is if you try to plot this, it looks something like this. Let's say, what is the maximum value that false positive rate can take? It can take 1, right? It can be 100%, right? So 100% in terms of numeric is 1. If you are getting 100% of false positive rate, it will be 1. And if your rate of true positive is what? 1. That's the maximum that it can be. And here it is 0. Okay. So this is the value that you can get. Correct? I've just drawn a dotted line. Okay. Now, in reality, if you try to, iterate on all the thresholds, okay, this is how things will look like. Okay. This is what are you measuring? You're measuring that on this, let's say your false positive rate is 10%, 0.1. What is your true positive rate there? If you try to map this, this is what you will get. Let's say this is 0.4. So your error is less, 10%, but your predictions, your true positive rate is also 40% only. Correct? The idea is that you want to maximize your true positive rate while minimizing your false positive rate. Okay. So in that case, isn't this that value? Let's say this is 0.2 and let's say this is 0.85. Isn't this peak that it is taking the best one? Because over there, your false positive rate is 20% and your true positive rate is 85%. Correct? 0.3, 0.1, whatever. Okay. And please share the notebook. Sure, Leslie, I will. And there was someone who wanted me to do the image part again. We will move on to the collab only after this. So I'll do that once again. Okay. Anyways, we will be plotting this also in the notebook. So I'll take it there. Okay. First, just concentrate here and understand what we are trying to achieve. But can someone also tell me that the value, if I try to take from here, will be somewhere around 0.92? Then why not choose this point? I'm getting a better TPR, right? The true positive rate is better there. But still I'm going with this 0.85. Why? But FPR is high. Exactly. Okay. So the trade-off, there is a trade-off. If you try to plot it here, this will also be somewhere around 0.65. Right? You know, we have to increase our TPR, but we have to also keep FPR minimized. With this trade-off between 85 to 92, see how much of an error we are increasing. So that's why the closer it is to FPR, least FPR and maximum TPR is the way to go. So this is not right and this is correct. Is that clear? CLR, is that clear? We want FTR less. It is FPR. Okay, cool. So what you have studied, guys, is called ROC. Is called ROC. And ROC stands for Receiving Operating Characteristic. How this name came and why, I have no idea. They have, taken this concept from, I can explain, but I don't want to go there because it will be digressing from machine learning a lot. But the concept is coming from your electrical field, okay? Electrical engineering field, where they look at, how, and, over there also we have something on the transmitters, if I'm not wrong, transmitters or transformers. This is the same graph that we get there. So that is why it is called the ROC. Okay. Now, since you have understood what is your ROC, let's move on to another thing, which is very simple, Let's plot the ROC again. Okay. This is your TPR. This is your FPR. Okay. And this is 1. This is 1. And we will try to map it in here. Okay. Now, this is one of the models that you have tried. Okay. And there is another model which works like, okay. And there is this. Now you have to tell me one, which is a better model. Let's say this one is M1, this one is M2, and this one is M3. Yellow one, M1. Is M1? M1. Okay, cool. That's right. M1 is the best model. How did you decide that? You looked at this value. You looked at the trade-off between your TPR versus your FPR. Here, this is the value of TPR, correct? And this is the value of FPR, correct? This is for M1, and this is for your M2, right? So obviously M1 is better. It has lesser FPR. So for M1 is best model, correct? But what is this M3? Remember in linear regression, we compared our model with the average model. This M3 is nothing but random model. Meaning, if you don't do anything and randomly keep saying yes, no, yes, no, yes, no, no, yes, no, yes, in a random fashion, you can go ahead and check this mathematically also. This is the line that it will give you. Okay? Okay? Now tell me one thing, guys. If you have this another model, which goes something like this. Okay, let's say this is M4. What can I say about M4? 50-50, yes. Red line is your random model. It's 50-50. What can I say about M4? M4 is worse than random model also, right? Which is very sad. Even if you randomly do things, ever, if you have built a model which is M4, which is underperforming than your random model also, which is M3, then that's not the right model, correct? You're even performing worse than random model. What's the point? Your model is predicting even worse than guessing, correct? So M4 is a big no. Okay, is a big no. Everyone understands. Everyone understands that. Okay, cool. Now, how there is another metric to compare. It is coming out of this only. Okay. Now, can I just copy this and somehow explain that? Let me do that. I don't want to. Let me try to do all this. Now, can I say, this is the area under curve? Can I say this or no? For model M1, isn't this the area under curve? You get the idea. I'm not able to color it properly, but you get the idea, right? For the green model, what would it be? For the green model, I'm just removing this. Will this not be your area under curve, right? So can I say that area under curve, area M1's area under curve AUC is more than M2's area under curve, right? This is how you compare. Okay. So if a model's area under curve in the ROC graph, okay, is more compared to the other, then you say the model which is having the highest area under curve is better model. Okay. And this will always be less than 1. I'll tell you why. So let's take the same value. Same thing. This is your TPR. This is your FPR. Here you have 1. Here you have 1. When I joined this, remember, I drew this in the beginning. This is what? Can I not say that this is the total area under curve, right? And what is this? What is this? This entire width is 1. This is also 1. So area of square or rectangle is what? 1 square is 1. Okay. So the maximum area under curve is equal to 1, and probably your M2 is around 0.83, and your this is M2, and this is, let me complete this first, is around 0.63 M1. Is that clear, guys? So this is the better model. Okay. So this in short is together called ROC AUC, which is nothing but, this is your receiving operating characteristic, and this is nothing but area under curve. Cool. Okay. So this is how you compare the models. Okay. This is how you compare your models. So now let's dive into the code and see how can we get ROC there. Any queries before we jump in there? So now let's go into the hands-on and see that for our model that we have already created. Okay. For our model that we have already created, what does the ROC looks like? Okay. And we will also create this again, right? We have stored the confusion matrix here in CM, correct? Now let's go and do this again. Let me take my keyboard. Let's do this again. So from sklearn.metrics, I'm doing that again, but you need not. We've already, imported it. Import confusion matrix display. Okay. Confusion matrix display. Once you do that, you call that confusion matrix display. You pass in your, this is only for display. You have to pass in your actual confusion matrix here. You have to pass in your actual confusion matrix that you have stored in CM. Okay. So you will pass this CM and you will say dot plot. Okay. And here on the side, it is saying no true label means the actual. Here it is saying predicted label, meaning the predictions. So you have predicted 0, but it is a 1. You have predicted negative n, and this prediction is also wrong. So this is Fn. This is Tn. For ROC curve, sklearn has made it so easy sklearn has made it so easy. It has done all the heavy lifting for you. It has done all the heavy lifting for you. So what you'll do is from metrics, you will import ROC curve. Okay. And you will also capture the ROC score. Okay. After you do this, now pay very, full attention here. I'm guessing there are no queries. I'm just looking. Cool. All right. So once you do this, what you have to do is there is this function called ROC. Now, whenever you don't know, I'm just showing this. How do I add a tab when this is not there? I want to add a new tab, but I am unable to because this thing is coming in front of me. Okay. So whenever you don't know what is happening, okay, go to ROC curve. Okay, just take a guess, guys. Will ROC curve here, let me go back to there. Will ROC curve accept what values as arguments? TPR, FPR. Okay. What else? Any other guesses that it might take? The FPR and TPR. But let's see. What does it take? Go to the scikit-learn documentation. What does it take? It takes your Y true and Y score. Okay. This is not saying Y predictions. This we understand is your Y test. But what is this Y score? Let's look at this. Probability estimates. These are your probability estimates. So how do we get the probability estimates? So I just want to look at, we have the log model, right? I want to see if it's already there. Yes, it's there. So here, let me show it here itself. So when we wanted to predict the label, right? What did we use? We did Y test, correct? Correct or no? And what did it do? Log model dot y, it's X test, right? We passed in the metrics and it gave us what? 0 and 1, correct? It gave us 0 and 1. There is another thing which is log model dot predict dot underscore proba. Yeah. What will it give us? It will give us the probabilities. Let me save it here. Probabilities is equal to predict proba, and we have to pass in the X test. Okay. Let's look at these probabilities. Rather than having this 0 and 1, it is giving me probability. Till now, we have understood all the probabilities in logistic and everything, right? So this first one is 0. Second one is 1, correct? So that's why this target is becoming 0 because there's 99 probability. Thus, this will become a label 0 and there's only 0.005. And here it's 0.79% probability that it will become label 1. And this is 0.2 that it will become 0. That's why you see 1. It is automatically doing that for you. So if you have to look at the probabilities, you have to look at predict underscore proba. But if you wanted to only be what? The labels based on 0.5, you will do only predict. Now you know how the logistic regression is putting the probabilities. Okay. Now this is what we need to enter here, the probabilities. Now let's do that. Okay. So here, and what does it give us as an output? It returns FPR, TPR, and the thresholds. Thresholds are the thresholds that we have to decide. Okay. Either 0.5, 0.4, 0.3, which one is better? So we will do this. We will first is FPR, then TPR, then we have thresholds, then we are going to call ROC curve, and what was the first input? The first input was Y test, and then the other one was probabilities, and what was the other one? Labels and all. Okay, that's fine. We can run it with this also. Okay, but now your probabilities is having two columns. right, is a list with having two indices. This one, first one is always related to 0. The second one is always related to 1. So in general, everyone is trying to do 1. So your case is that you need to detect spam, which is 1. You need to detect people which are having cancer, is 1. Okay. People, what example did we look at? Fraud. Are they fraud? 1. So this is what we are going to pass in probabilities. We are going to pass it the probabilities of whether it is a spam or a not spam. Okay. So we are going to pass all the rows, but the first column 0, 1. And let's see what it, let's run this first. Okay. Now we know what is FPR. Let's print it out. There are so many values, right? For each threshold, it is trying to do that. For TPR, so many values, correct? Now, the point is that we need to plot the ROC curve. How do we plot it? We will plot it using plot figure, and then we will do PLT dot plot. We have to pass in your FPR and TPR. Then the other labels and all I will show, but I think let's do this first. Do you see the ROC curve? Let me, put in these labels so that it is much more clear. True positive rate, and let me put what title ROC. Okay. So is this clear now? This is your true positive rate. This is your false positive rate, and this is your ROC. Okay. So in our case, the problem that we have solved, isn't this the one that you're looking for? If your FPR is what, 40%. So that will come from business, that what is an acceptable range of FPR, or based on your use case, you would know that this is not acceptable. This high is not acceptable. Anything between 0.4 or less than 0.4 is acceptable. Anything which is less than 0.1 is acceptable. Anything beyond that is not acceptable. Okay. So you will get this. Now let me also plot this. PLT dot plot. Let me also plot in. So what is this? The value that your red line, the random model can take what? X-axis is 0. The first point will be 0, 0, and second point would be 1, 1, right? Second one would be 1, 1, right? And we will make it as red dash line. So this is your random model. Okay. Now we will also look at the area under this curve. So the area under this curve would be what? ROC, AUC score, and then we will pass what? We will pass Y test, and then this is my predictions. My predictions were Y pred 73.6. So you know the area under curve now. Is everyone clear now? I know I'm making so much of typos. I don't know. I've got this new keyboard, probably because of that. If ROC covers more area, then model is good. Yes, yes. And generally, the way things are done, you will always have this peak somewhere. Okay. For all the lines that you'll be drawing here, you'll be having that. Okay. Cool. So now we've covered ROC. We've covered ROC under the curve. And now we'll move on to what? We have finished logistic regression. What are the limitations for ROC curve? See, I cannot cover 100%, but in ROC, there are a certain limitations. Okay. There are certain limitations. That's why we go ahead. We also somehow look at, it's not limitation, it is requirement. Okay. I'm covering this, but is there any alternate? Yes, yes, there is. Let me go back and explain this. Okay. So here, what happens is, now we've looked at ROC under curve. Anywhere under ROC, we are looking at TPR and we are looking at FPR. Are we looking at the negative predictions? No, right? We are not looking at true negative predictions, the true negative rate, meaning we are looking at the emails that were correctly specified as spam, right? We are not looking at cases where how well are you doing when you are not predicting the non-spam as not spam also. That is your true negative rate. Okay. We are not looking at that. But in some cases, when that is also a metric to look at, we are only concerned about if my true positive rate is better. Okay. I'm able to identify the fraud. I'm able to identify the spam. But there is a very small, idea that you, in some cases, rarely you would also want to look at how well am I doing on the other side also, on the other label also, which is your true negative rate. That's when your ROC, AUC will not, kind of come in handy. Then you have something called as PR curve. And this is nothing but this is your precision recall curve. All the concepts are exactly the same. All the concepts are exactly the same as ROC. Okay. Here you will have precision. Here you will have your recall. Okay. And the area or this is how in that case things will look like. It something looks like this. Okay. You need to find something which is having precision also high and recall also high. RE also high. Okay. Every concept of ROC is exactly the same. It's just that your y-axis and your x-axis has changed, and this is a mirror image because over there precision will be high, recall will be high. That's the motive. Okay. Okay. But this is not good model. Exactly. So if you had looked at the accuracy, did we print that? Let me see. Okay, let me print in the accuracy also here. So the accuracy of the model is also coming from sklearn dot metrics. We do what score. Okay. Now it's already there. So let me do log model dot score, and I will pass what my, this is the, if you look at the data set, this is the accuracy that you'll be getting. This is the accuracy that you'll be getting. Okay. In this case, what has happened is your AOC curve is also similar to this. But if you look at some other cases, your accuracy, especially when the data is imbalanced, your accuracy will be very high, like 95%, but your area under curve will be less. Your precision will be less. Here, look at the precision. Where is that? Here. Look at the recall. Okay. Look at the F score. So you have to look at all these things together. Since our data set was balanced, it was an imbalance. You're not seeing very different things, right? Model is bad. The thing is, you need to go ahead and do some changes in your model now. You need to try to remove some columns. You need to try put in some more features for it to improve. Okay. That's the idea. We are doing one pass, but you know what the next step is. How we can make good model in this. Go try, remove a few columns, do some data exploration, try to do some manipulation, give it a shot. Okay. That's how we learn. See, I'll tell you what, practice is what is, very necessary. I can keep on doing these things. Okay. And you would feel that this is very easy. This is very easy. I'm telling you an honest thing. Okay. But when you try to do it, you'll find hundred of errors. You'll find hundred of questions. That's where the learning is happening. That is where learning is happening. I showed you how much time do we take for, making this model. There are steps that we already know. How different is linear regression with logistic regression? It's the same steps, correct? Everything is already done in that library. So until and unless you practice, guys, things will not be 100% clear. I can clarify all your doubts. I can clarify all your logic. I can show you the hands-on. We can do this together, but maximum learning will happen when you do it at your end. You need to do things at your end. Okay. Take at least 2 data sets. Take at least 3. There are so many data sets on the internet. Try running linear regression. Try running logistic regression. We've done both of them, right? Make some changes in the data sets. Make some changes. Do something new, right? That's where the art is coming into the picture, right? You can create the model, you can evaluate the model, but then next, how to improve the model, that takes skills of different level, and that comes with practice. Okay, cool. See, Anvesh, gradient descent is an optimization, right? So internally, what it will try to do is it will try to reduce the error using the optimization algorithm, right? This thing that we are looking at, this thing that we are looking at for increasing model accuracy. Huh, but see, gradient descent will work if you have given, I will explain this with an example. So if you have given four columns, four independent features, okay, and you're trying to find the best M or C in linear regression, okay, for those set of input features, those set of independent features, it will give you the best M and C, correct? But it is your job to go back and see that what if I give only three columns? What if I give only five features? Then when you pass it, then gradient descent will look at those five and give you the best M and C in linear regression. And then you need to compare that adjusted R square exactly is better than what you were getting with four features. Okay. Gradient descent is working underneath already, but you need to give a different input for it to work differently, to it to further reduce the error. Okay, perfect. Which is naive Bayes. Okay, so this is used for classification. Okay, and these two words, this Bayes comes from Bayes theorem. Everyone who knows Bayes theorem in probability or has heard about it, I don't expect you to remember it, but have you heard about Bayes theorem? Not for. And naive. What does naive mean? Does anyone know what does naive mean? So in Hindi, if everyone knows that, it is bhula. Okay. So this is the meaning of naive. Okay. Lack of experience or judgment. Very innocent. I would say innocent. Okay. Is innocent. Okay. Bhula. If you know this term, or innocent. Very naive, is beginner kind of thing. Very simple. So now let's understand this, why it is called so. Okay. Bayes theorem. So basically all of this is under probability. Okay. We looked at logistic regression. Okay. We looked at odds, we looked at log odds, we looked at probability, how things are different. But Bayes theorem is specially based on the naive Bayes is specially based on Bayes theorem. Okay. And this innocent, I'll come to this, why it is called this naive, but that is one of your interview questions. Okay. This is an important question. What is naive about naive Bayes classifier? Okay. This is something that you need to know, guys. This is something that people generally try to ask. Okay. If your interviewer is in the right state of mind, this might be one of the first questions to test your basics around naive Bayes. We'll come to this. We'll answer this. I want to give you the opportunity to look around this, but let's go more onto this technical term, which is, Bayes theorem. So all my non-math background friends and non-tech background friends, just trust me. And what I'm writing here are pure simple formulas, pure simple, properties that have been defined. Okay. We are not going to derive anything, but it is something that is already existing in mathematics. We cannot learn, unfortunately, we cannot learn naive Bayes without going into maths. Okay. Because the whole funda is around probability and mathematics. Okay. So I'll tell you, I'll try to simplify as I can. Okay. The more I can, I'll try. But this Bayes theorem, okay, is told as if your probability of getting, this is what? This is probability. We know this is telling me some probability, correct? This is
And what is this? This is event A. This is event B. Correct? What is this? What is this? What does this mean? Unrelated kind of that, but yeah, I'll tell you. We'll capture it. So this, in short, is called, how you would read this is probability of A given B has occurred. Okay. Meaning, what is the probability of A if B has already occurred? Okay. That is what this tells me. A is event A, B is event B, P denotes probability. This sign here is not of division. Okay. This is not of division. This is how you would read it. Okay. Probability of A given B has already occurred. Let's take an example. Imagine you have 5 red balls, okay, and 4 yellow balls, okay, in a box, okay. And now you have to tell me what is the probability of getting a yellow ball, what is the probability of getting a yellow ball, and what is the probability of getting a red ball. So this is 5, this is 4, and total is 5 plus 4, 9. What is the probability of getting a yellow ball? 4 by 9, 5 by 9. Yes. Okay. So this is 4. We have 4 here, and total is 9. So it is 9. Okay. And this is 5. Total is 9. So 9. Okay. Now, what happened is one person has already taken out a yellow ball. Let's say, so Lakshmi has already picked one ball, and that ball is yellow. One. She has already picked from here. Okay. Now you have to tell me what is the probability of getting a yellow ball given this event. Let's call this event as D. Okay. Given D has already happened, or let me write it in a cleaner way, that Lakshmi has already picked one yellow ball. What is the probability of getting a yellow ball in that? Probability of getting a yellow ball when Lakshmi has already picked one yellow ball out of the blue bag. 3 by 8. 3 by 8. Good. You guys are smart. It is 3 by 8. How did we get here? How did we get here? Let's try to do this step by step. Okay. So let me copy it here. This is your step 1. Step 1. This is what you have. Correct. Then what is step 2? What happened? Lakshmi came and I didn't realize I'm skipping a word, skipping a letter. Lakshmi came and she picked one yellow ball. When this happens, how will your system look like now? How is this bag going to look like? Isn't this system going to look like this? That she has already picked one ball. So how many balls are now left? In yellow, balls are left are 3. And how many total are left now? 8. Correct? So what is the probability now? That's what you were saying, right? 3 out of total 8. So this is the probability. Okay. Everyone with me? I've tried to explain it as easy as I can. You have considered that one event has already happened. Lakshmi has already picked one yellow ball. So your blue bag will have now 3 yellow balls and will have the remaining 5 balls because remaining 5 red balls because nothing has been done to that. And now your total will be 1 less because one ball has been taken out. Okay. What will be the probability of getting a red ball when Lakshmi has already picked one ball, already picked one yellow ball? Can you guys help me with this? What is the probability? Correct? Correct. 5 by 8, right? Because now you have 5 balls and total is 8. Okay. So that's why it is 5 by 8. Now hold on to your seats. Okay. Hold on to your seats. So Bayes theorem is nothing but, this is a formula. Okay. This is a formula for Bayes theorem. Bayes theorem says, okay, that probability of A given B has occurred is equal to probability of A, okay, into probability of B given A has occurred over probability of B. There's nothing fancy in this. This is the formula of Bayes theorem. Okay. For you to predict or to get a probability that A has occurred after B has already occurred, you can calculate it by using the probability of A individually into probability of B happening when A has occurred divided by probability of B. Okay, this is the Bayes theorem. Okay, everyone with me. I know you will not remember this formula, but at least for now, you saw the formula, right? Correct? Some 11th, 12th, 10th marks maths is coming up to your mind, even 9th standard, 10th standard probability. Okay, you used to solve this. So now, if I say, how do we take this concept for our machine learning data set? How do we apply this here? This is really the crux of it, guys. Okay, this is really the crux of it. You need not spend any other video or any other literature on this. Just pay 100% attention and it is going to be super clear. Okay, so imagine you have this data set. Okay, this is your y, which is your target variable, and this is your x, which is your independent. Okay, and you're having feature 1, feature 2, feature 3, and so on. Okay, and you have only one target variable, correct? So how, if I want to know the probability of y given x, probability of y, which is your target variable, given x, how will you calculate it? How will you calculate it? Now, you know, you have to somehow get a probability whether this comes in 0 or y or a 1, which is your y, given x has occurred, meaning some feature, feature 1, feature 2, feature 3, given these are the values, what is going to be my y? Can I say, understand this as that? Let me write that. What is the probability of y, okay, given it has seen features f1, f2, f3, and so on, which is nothing but your x. Can I call it like this? Right? And from Bayes theorem, you know that probability of y given x has occurred. When you say occurred, meaning the data is already there. In heart attack data, you know the cholesterol was 240, for example. You know the age was 61. So it has already occurred, right? So in this case, it would be probability of y into probability of x given y over probability of x. Correct? Acts like target variable correspondingly. Yes, yes. Okay. Now, what is this x? We know x is nothing but is a combination of feature 1, feature 2, feature 3, and so on till n features. Correct? Okay. So, can I write this above equation like this? Let's say this is 1. Okay. This is 2. Can I write 1 as this? That probability of y is nothing but when feature 1, feature 2, feature 3, so on till feature n has occurred. Can I say this? And just imputing the values of x. Can I say this? It is nothing but probability of y into probability of feature 1, feature 2, feature 3, so on till n features, given y has occurred over probability of feature 1, feature 2, so on till feature n. Have I done anything different? Have I done anything different? I have just used this and put this value here. I have just used this and put the value of x there, right? I hope that's clear. That's very simple. Third, now the other property of probability is if A and B are independent, then probability of A comma B is equal to probability of A multiplied by probability of B. This is the property. This is the rule. If A and B are independent, correct? Meaning occurrence of B does not influence occurrence of occurrence of A, then these two are mutually independent. Okay? They're independent. So this is how you say. So now we know our features 1, feature 2, feature 3 are independent. And that is where naive Bayes is kind of naive. Okay? It assumes that all the features are independent. Okay? It assumes without looking into anything, very innocently, it will say whatever features that you're giving, I am assuming that they are independent to each other. Okay? Which may or may not be the case. That is a different thing. Okay? That is the assumption that naive Bayes works with, that my features are independent. So when they are independent, can I now break the above equation like this? given feature 1, feature 2, so on till feature 3 is nothing but probability of y multiplied by probability of feature 1 given y has occurred, multiplied by feature 2 given y has occurred, and so on till probability of feature n given y has occurred, divided by probability of feature 1 into probability of feature 2, and so on till probability of feature. Is this clear, guys? Right? We are using just this rule, and we are saying we are imputing all the values, that probability of feature 1, feature 2, feature 3, feature 4, feature 5, all of them occurring together given y has occurred is equal to probability of feature 1 when y has occurred into probability of feature 2 when y has occurred into so on. Okay, this is how you apply naive Bayes to your data set. That's done. It's done. Naive Bayes, in naive Bayes, if you understand the base part of it, there's nothing crazy about naive Bayes. It just works on probabilities. And this will now tell you what? Whether your target variable, it will give you a probability whether given all the features, your y is 0.33 or 0.78. If it is 0.78, let me give you an example. Okay. If this comes out to be 0.33 or this comes out to be case 1, case 2, this comes out to be 0.78, then what is your prediction going to be? In this case, it is going to be 0. In this case, it is going to be 1. Correct? Right? Remember the spam and not spam? Remember this graph that if it is 0.5, this is going to be 1. This is going to be 0. Given the threshold is, if it is greater than 0.5, it is going to be 1. If it is less than 0.5, it is going to be 0. Remember this? That's what we are doing. Have we done anything new? Right? This is what your prediction will be, no? And ultimately, what you have to do? You have to predict the label only. Even while doing logistic regression, we looked at predict probabilities. It was having probabilities, right? So what did it have? It has, if the probability of having 1 is 0.78, probability of having a 0 is 1 minus 0.78. Okay? Is that clear, guys? Internally, I showed you in logistic regression when we were doing, okay? I showed you. Let me go back there. This is for our understanding, okay? Internally, I showed you the probabilities. Where are the probabilities? Oh, I showed you, no? I told you the probabilities is 0.99, 0.005. So if you sum these two, it will become 1. So the probability of it being 0.99 is 0. Okay? Correct? If it is that, then you're going to say 0. Okay? So this is where this is slightly different, how things are calculated and how it is there. So I explained you with 0.5. That is what you have to remember. But mathematically, what is happening is it will tell you the probability of it having a 0 is this. Probability of it having a 1 is this. Okay, got it? That's why we are saying even if it is 0.33, we are saying it is 0. So we will say this is nothing but, this is nothing but, this is nothing but, you always predict the probability of 1. So this is telling you probability of it being y is equal to 1, which is 0.33. So what is the probability of being a 0? 1 minus 0.33, right? And this is also telling you probability of it being a spam or y is equal to 0 is 0.78. That's why you're going to say it is 1. This small minute difference, this 0.33 tells you its probability of being a 1 is 0.33. So what is the majority probability? The majority probability, which is 66% or 67%, is of it being a 0. That's why we say it is a 0. Okay? Little confusing. Yes. So you have to not confuse. I'm telling you here now so that you can clarify it here. Okay? so that you can clarify it here, because I'm already assuming and treating you guys as data scientists and machine learning engineers. You're just learning on concepts. Okay. I'll explain it once more. So when we did predict underscore proba, it gave us what? It gave us probabilities, correct? It gave us probabilities, and the probabilities were looking like this. This is 0 and this is 1. This was what? 0.99 and this was 0.01, correct? And then what about the next one? Let's take our example, 0.33, 0.33, and this is 0.67, and this is 0.78, and this is 0.22. Okay. This 0.33 is nothing but this. This 0.78 is nothing but this. So when it is very low, 0.67 is 0, right? So it will be 0. When 0.78 is more, greater than 0.5, just remember greater than 0.5. Okay. It is 1. Okay. Cool. Third case, anyone would have asked me, could be that it is exactly 0.5. What would you do in that case? What if it is 0.5? Nothing. It's a 50-50, right? It's a 50-50. So no one is going to question you whether you're saying that 0.5 should go to 0 label or 0.5 should go to 1 label. It is your choice. Okay. And it is also the business choice, because it has equal likelihood that it could be a 0 or it could be a 1. It could be a spam. It could be a not spam. It could be a fraud. It could not be a fraud. So depending on the situation, it could be a cancer. It could be a healthy person. Depending on the situation, if you are more conservative, meaning you want to, say that even if, someone gets 50% chance that of that person is a cancer patient, you will say that it is label 1. Okay. So in that case, you will say 0.5 is 1. So it depends. It is 50-50. It is right on the edge. That's why it is 0.5, right? 50%, 50-50. Okay. That's why I'm not talking about it, but it is widely accepted. It can be either here, either there. Perfect. Now, this I have just said here to connect it with predicted probabilities, how it comes in the code. Comes in the code or sklearn. Okay. This comes from logistic regression. Example. I've just given you an example that you shouldn't be like, you're saying 0.001 and you're saying that it should be label 0. It should be, but you should be looking at only this then. You shouldn't be looking at probability of 0 and saying that it is 0.99 and I will mark it as 1. That is the confusion I wanted to clarify. You need to be very clear that you're looking at this value. You're looking at probabilities of 0 given y has occurred, or you're looking at probability of 1 if y has, if all the features has occurred. That you need to be very clear. Here we are looking at probabilities given y is equal to 1, given it is positive, TPR. Okay. So that's what I wanted to clarify. Cool. Now we have done this. Let's do one example, which is what? Practical. So I have already created a data set so that it's easy. Okay. So we will do one practical example. We will do one practical example how naive Bayes works. Okay. Of how naive Bayes classifier works. Let me put this example here. Yes, I have it. Okay. This I have created a data set. This is your feature 1. Let me call it x1. This is your feature 2. Okay. And this is your target variable. Okay. So it says, how is the outlook of that day? Meaning it is rainy, it is overcast, it is sunny, or something else. Is there anything else? No, right? And how is the temperature? Temperature is hot, mild, or cold. Okay. And given these two features, will you play or not play? That is given here. No means no. It's not a good time to play, not a suitable conditions to play. And yes means it's a suitable condition to play. Data set, correct? Okay. Now We have to do what? Now you have to tell me how many. We are going to look at Outlook first. We are going to look at Outlook, and this is sunny. How many unique values are there in the Outlook? Come on, guys. I need you to be very interactive. I have not done this. I want to do this with you. Rainy. And what is the other unique value? It is overcast. Correct. And how many yeses are there here when it is sunny? How many no's are there when it is sunny? Tell me. So when it is sunny, how many yeses? Three, is it? And how many no's? How many no's? Two. Okay. And when it is rainy, how many yeses? So when it is rainy, how many yeses? Do I see any? I see one, two, right? Okay. Similarly, rainy and no, how many? Rainy and no. One, two, three. Okay. Overcast and a yes. Overcast and a yes. Three or a four. Weird, right? Data set is weird. When there is overcast, people are playing. And when overcast is there, how many no's do we have? Zero. Correct? Now, if this is your attribute, let's say this is your attribute, Outlook attribute. Okay. Can you guys tell me, based on what we have looked at till now, what is the probability of a yes given an attribute has occurred? Meaning, what is the probability? Let me hide this. What is the probability that it is yes when it is sunny? Or before that, let me do this. Let me do this. Let me do total. What is the total? 3, 4, 7 and 2, 9. Okay. Yeses are 9 and no's are 5. Correct? Now, what is the probability of a no? Will this probability yes and this box would not mean 3 over 9? Sunny and a yes. Correct? No, sunny is no and total 2 by 5. What about rainy? 2 by 9. Overcast 4 by 9. Tell me this, guys. Probability of rainy, probability of no here in this box when it is rainy. 3 by 5 because no is a 5. Okay. Let us now fill this 0 by 5. Okay. And this is 100%. This is 100%. Okay. Now to make things quick, we will also have to do this for temperature. Okay. We will also have to do this for temperature, and temperature is what? Hot, cool, mild. Okay. Here we have yes, no, then we will have probability of yes and probability of no. Okay. To do things quickly, to not waste time in this, we have done one. I have it here. So let me pick this, this, and this, and let me copy. Let me come back here. Okay. So we have everything here. This is what we saw for Outlook. There is one mistake that I'm noticing now. This is 3 and this is 2. This is 3 by 9 and this is 2 by 5. Correct? Correct, right? That's what we calculated. And I'm putting the temperature one here. And this is nothing but probability of yes or a no. Total yeses are 9. Correct? Out of total, how many are this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You can do a total sum from here also, but I wanted to show you guys. Okay. Is the data set clear? Perfect. Now I have to find. Now, whatever we did earlier, we have to do it here. Okay. So I have to find probability of playing. Yes is a playing. Okay. Probability of playing given it is sunny and hot. How can I do this? You understood the problem, right? Y is nothing but play, golf. Are you able to understand? Is this making sense? How naive Bayes is working on your data set? You have to find the probability that it is likely to play given it is a sunny and a hot day. Use Bayes theorem. Exactly. So we are going to put Bayes theorem into place. So we are going to say probability of Y given sunny and hot is nothing but probability of Y into probability of sunny, given it's a yes, multiplied by probability of hot, given it's a yes, divided by probability of sunny over probability of hot. Is this clear, guys? Is this super clear? What do you have to do now? You have the probability of Y, you have the probability of sunny, you have the probability of sunny and a yes, you have the probability of hot and a yes, this one and this one and this one. Can't you put the values here and solve it? Correct? Will you be able to? Will you be able to do this? Okay. And similarly, you can also calculate probability of not playing given it is a sunny and a hot day. This only, right? It's just that Y will now become yes, Y will become no. Correct? And you'll take the opposite values. Okay. After you put in these values, this thing will come down to be somewhere around 46% or 45%. Okay. And this will come down to be somewhere around 55% or so. Okay. Or in other words, it is going to be 0.45 and this is going to be 0.55. Okay. Depending on what is your target variable, you are going to predict what? This is more, right? Probability of not playing. So you will predict 0. You will predict don't play, which is 0. 1 was play, right? Cool. Perfect. You have by hand manually calculated naive Bayes with an example, with a life example. This is what the model is doing internally. Understood? So once you understand linear regression and logistic regression, you understand the concepts, then things are simple. And especially this naive Bayes. Naive Bayes is so simple that it is so mathematical that you can calculate it. Okay. Clear, guys? Okay. So I think we are going to start something really cool. You'll enjoy. So we are going to start new family of algorithms, which is nothing but tree-based algorithm. Tree-based algorithms. Okay. And here particularly we will be looking at decision trees. Okay. And we'll also be looking at random forest. Okay. These two are very similar in terms of context and in terms of how things work. So we'll look at decision tree first. From there on, explaining random forest will not be difficult to even understand. It's just a broader concept of decision trees. So let's start with decision trees. Okay. Now, what do you understand by this term? Decision tree. Tree is nothing but a structure, right? Something like this, correct? It is symbolic of a structure. And this is something that helps you to decide, right? So this, I can say some rules. Okay. The rules that help you to decide. Okay. Now, interesting thing about these is, in fact, all the tree-based models is, it can be used for both classification and regression tasks. Isn't that cool? Isn't that cool? It can be used for both. It can also be used for classification. It can also be used for regression, predicting yes or no depending on one by one model. Okay. And then break down a problem into smaller. So we can say the same thing for logistic regression, right? Or naive Bayes also. It's breaking down the problem into smaller ones, or, depending on one by one, we are trying to, say whether it is yes or no. So very broad. In general, this is what decision tree is about. Okay. Main thing to take away from here is rules and this structure. Okay. And the main thing, the most important thing is that it can be used for both classification as well as regression. Just give me a second, guys. Yeah. Okay. So that's the main thing. That's why, these all decision trees, random forest, all your tree based algorithms are so popular because it's so intuitive. It's so easy to understand when you're working on a problem in the real world, in the industry, when you're working on a problem. It's very intuitive in terms of explaining to the customer or your business or, for whomsoever you're doing this work, be it your boss, be it someone who doesn't understand machine learning, given the output. Okay. It is easier to explain to them that this is how you're getting the results. But for you and me, who are in this line of work, which is machine learning engineers, data scientists, or AI engineers, all these people, we need to know a bit more, right? We need to know more than a normal person knows, right? That's when we can explain it in a normal fashion, right? So that's what we are going to cover here. We are going to uncover some of the things that most of the people don't understand. Okay. But why the name trees? Why the name trees? Okay. So it comes from nothing but, if some of you are from computer science background or even the tech background, you might know there is a data structure called trees, right? There are some data structures that are tree based, like the binary tree, red and black trees. Okay. Then you have n array trees, all these. Okay. But that's why how decision tree works is based on the tree. Okay. So that's why the name comes as tree from there. Now, to understand this tree, you have this one. Okay. And this is how the tree looks like. Okay. This is your root node. We call it as root node. Okay. And everything which is yes, you will have some rule here. Let me write it with, you will have a rule here. Okay. And anything that follows that rule, okay, anything that satisfies that rule comes in your left, in your yes. Yes is always on the left. Okay. And this one, which doesn't satisfy that rule, is on your right. Okay. This is an example of a binary tree. That's how things look like. Okay. Now let me understand. Now, once we know this, let us understand more from the intuition side. Okay. Tree is this, but how does it work in reality? Okay. Let me create a data set, and from there we will, look at how to go about things. Let's take an example. Okay. Now the problem is you need to find employees in your company that are going to leave. Okay. Imagine you work in a really big MNC. Okay. And you want to find people who are going to leave your organization or are going to switch or are going to do something, change their jobs. How will this help? This is going to help if the employee is really good and you want to hold them, you want to, keep them back. You will probably, give some increment, some bonus or something or the other. Okay. That's how, and also it will help you to plan that, okay, I'm going to see a shortage of, let's say, 10 people who are going to leave. I need to hire 10 more people, right? That's the problem. So this thing is called employee attrition. This thing is called employee attrition. Basically, any employee, the rate at which the employees leave over a time, that thing is called employee attrition. And you need to find people who are going to leave. Okay. And this concept is called, okay, so tree structured model, yes, used for decision making. Exactly. Clustered index uses binary data structure. Clustered index uses binary data. So it's slightly different from there in here. Okay, you'll get the idea once we look at this example. So let me plot a graph for the same problem that we are looking at. Okay. Now the issue is that we are looking at age on the x-axis, and we're looking on overtime, the number of hours that a person has to do overtime. Okay. And that determines whether the person is going to leave or not leave, and also probably the age, right? Probably the age as well. Okay. Let's have it here, and then let me quickly plot the graph. Let's take this. So, okay. So these yellow dots are the ones that are going to leave. Okay. And I will have it somewhere here also. Okay. Based on the people who are having a high age, they are also going to leave, and the people who have really high overtime, they also will leave. And then let's also plot set of people who will not leave. Okay. So let us plot it here, all these people. Okay. Now tell me, you get the idea. You need to find people who are going to leave. This is just a similar example like attrition is an example like customer churn. Okay. You need to find people who are going to leave. Now, this is a classification problem. Okay. It is a classification problem. Yes or a no problem. Correct. It is a yes or a no problem. Yes or a no. Right. And I'm going to say all the folks, all the people which are with green, I'm going to say that, they are going to stay. Okay. They are not going to leave. And all the people which are yellow dots here in our example, they are going to leave. You understand the problem? We have to find attrition rate. So this we will keep as 1 and this we will keep as 0. Okay. Now tell me one thing. It is a classification problem. Okay. Let me give you a hint. Okay. I feel if I give you this hint, you can come up with something. Let me put this as 35. Okay. Let me put this as 29 and this as 3 hours. Okay. This is 29 years of age. This is 35 years of age. Okay. There is one predict probability, but how? Yes. Yes, you're on the right track. We'll predict probability. But until now, whatever you have learned, right? You have learned that there should be a linear relationship, right? If I had a problem, if my end, I cannot fit a line here like this, right? This will be your logistic regression line, correct? I cannot do that. I cannot also split something like this, that everything on the left is stay and everything on the right is leave, because then we'll be, misclassifying so many points, right? That's how logistic regression will work. Even if we try to put something here, it will not work, right? And in linear regression, in logistic regression, we cannot do this also, right? We cannot put a line, put a something like this, which is non-linear. Understanding the problem now, correct? Thresholds, no, thresholds will not also work, Lakshmi. So basically, this is where your tree-based algorithms, are really good. They're really good. Why? Because you see that there is no way that you can draw one single linear line. There is not a linear relationship between overtime and age, right? As the overtime increases, you see some people who are still staying back. Okay. As you see your overtime increasing, let me put a line here. You still see that some of the people are staying, which are green, and some of the people are leaving, some of the people are leaving. Correct? And here, there is no definition of age also, that anyone who is above 35 will leave. That is also not only true. You also have people who are less than 29, they also leave. But less than 29 also, there are some people who stay and some people who leave. Okay. So in these cases, okay, what can I say? Can I say, can I try to make a, tree here? Let's make a tree here, which is if I say my age is greater than 35. Okay. My age is greater than 35. Then I will say it is what? On the left hand side, what it is? It is yes, right? I will get what? I will get leaf. Let me write it with yellow so that it is. I will get all the people who will leave, correct? But then if they are less than 35, it is a no. I cannot still say that they will definitely leave, correct? This we have identified with this yes. This we have already done, right? Anyone which is greater than 35, they will leave. Correct? Everyone with me till now? Okay. Then on the no part, when the age is less than 35, when the age is less than 35, can I say that people with less than age 29, can I say people with age less than 29 and having an overtime of greater than 3 years, 3 hours are also going to leave? Then we will be able to identify this area, no? Correct? Understanding the rule, understanding how we are reaching that area, it's very intuitive, right? It's very intuitive, easy to understand, correct? But how do we put this in the tree? How do we put this in the tree? So, and we also need to identify these people also, correct? So how do we do that is, in the no part, there is another question that we can ask. We can say people with age less than 29, age less than 29, correct? People with age less than 29, we know it is yes is going to be on the left. But can we say something about people with no, like greater than age 29? Can we say something about this region? We already checked greater than 35. They are no here, meaning they are not belonging here. They are greater than 35 and less than 29, or is here, but are greater than 29. Less than 35 and greater than 29. Isn't that this area, right? What can we say about these people? We can say that they are going to stay. Can we or can we not? Okay. I hope this is now much better so that we make the tree also with along with looking at the data, right? Not leaving, correct. Less than 29 will leave due to overtime. Yes. That's intuitive also, right? People who are new into the job, they're young, okay, they can do overtime. But if the overtime is really huge, okay, greater than 3 hours, they will leave. And anyone who has aged a lot, okay, they are going to anyways, they have spent so much of time in the company, they're going to leave. Okay. But between this range, between 29 to 35, they don't mind doing overtime also above 3 hours. That is what we are seeing from the data, right? So here we have got all the people who will stay. But what about this? What about this region? We are still left with this region, right? This entire region. And how do we classify them? How do we distinguish between them? We say we have another feature, which is overtime. If overtime is greater than 3, then and no, this is no. This is yes. If the overtime is greater than 3, what do we have? People will leave. If the overtime is less than 3 and they're less than 29 years, then they will stay. Correct? Isn't that right? So essentially, these are the rules, and these purple lines that I was showing you is a step-by-step criteria that we created, right? At the end of the day, at the end of the day, you are going to look like this thing is going to look like your final, or your line is going to look like this. This is what we wanted, right? In fact, correct. Now you are able to identify everything with this tree, right? And this is nothing but, I can say this is a tree, correct? And what have you noticed till now? It's nothing but rule based. We made so many rules. We made rule, which is this: age should be, greater than 35. We can have some people which are going to leave, and some people we cannot decide about. Then we created another rule, which is this one, okay? Which is this one. And we are going to say that, that the age is going to be less than 29. If they are greater than 29 and, less than 35, we can still say that they are going to stay this period, this region. Okay. But then in this region, we can put another rule about the overtime and say that, if it is going to be greater than 3, they're going to leave. If they are going to be less than 3, then they're going to stay. Everyone with me? Do you understand this now? Right? Clear? Key things that, or, okay, let me put it as key things. What did you notice here? All these white lines, these are axis parallel. These are axis parallel, meaning either it is going to be parallel to your, either it's going to be parallel to your x-axis, this one and this one, or it's going to be parallel to your y-axis, this one or this one. This one is also parallel, correct? You cannot fit a line which is, at some angle with the axis. It has to be parallel to either x-axis or y-axis, okay? Because it's very intuitive. These conditions you can only put if you're looking at either y-axis or your x-axis, right? Both of these are your features, okay? You cannot say that, okay, if, when the age is this, do this. When the age is this, do this. You cannot create a line like this. You can create a line, you can create a boundary for classification like this white line based on multiple rules in multiple nodes, okay? So this is the first thing, that it is axis parallel. And the other thing is, isn't this similar to many if-else conditions? Isn't your tree like many if-else conditions here, right? If age is greater than 35, then do this. If age is less than 35, then we have already reached all the set of people. We have classified them well. No need to classify them further, okay? Then on the right hand side, if age is less than 29, we have not been able to classify all of them, then we need another condition, right? Isn't this like your if else? Yes, it is. Okay. So these are your key things, and you can create here a non-linear model. I asked you when we looked at this initially, can you create a logistic regression or naive Bayes? Naive Bayes still you can work with the probabilities and somehow get, but logistic will not work here, right? Logistic will not work here because it will try to fit a single line, single linear line, whereas your data is not having any linear relationship, correct? Okay, so these are the, no need to worry about to keep the dependent, independent variables in X and Y. No, it is required. It is very much required. Here, what was your target variable? Your target variable was this. Your target variable was attrition and outline. The overtime and the age. Both of them are your features. Okay, both of them are your features. You're creating some rules on your features. Okay, cool. You'll get a hang of it if you have understood the logic. If the intuition is clear that you know how things are working, I think you'll get the hang of it. Okay, no need to worry. Let me see what I'm okay. So now let me do one thing. Since this is if else, I can create another. Now you understand this. I can create another tree like this. This is your tree one. Correct? Since this is if else conditions, and you can write if else conditions in multiple ways, right? Having that thought in your mind, okay, let's create another tree of the same prop. Let's create. Okay, now we are going to create another tree. This is your tree 2. Now, instead of starting from 35, can I not say in my first age less than 29 and I will have all the yeses here, all the no's here. Okay. When my age is less than 29, I can create another here saying that, if over time is greater than 3, correct? If it is greater than 3, what do I have? If it is greater than 3, then it is leave, right? And if it is less than 3 and age less than 29, we are in this region, correct? So we are going to say that they are going to stay. What about this? Less than 29, we figured out. And greater than 29, we can have another node here, same, which is age greater than 35. Here, all the no's, all the yeses, and all the no's. When the age is greater than 35, sorry, all the yeses, it's going to leave. People are going to leave. And when the age is less than 35, which is no part here, they are going to stay. Same rules, but the structure is different. Right? Same problem, same solution, but your if else conditions are different now. Now you started with age 29. Earlier you started with age 35. Correct? Different. No, same features. Tree 2 is also with the same features. It is nothing like, let me explain this with a if else condition. If age is, or what is here, greater than 35. If age is greater than 35, okay, then what will you say? Then leave, right? And then what will you say? Else if age is less than 29, what was it here? Age is less than 25, right? If it is less than 25, then it is going to be another nested if else, right? Inside this, there's going to be nested if else. If over time is less than 3 or greater than 3, what have we put? I just want to greater than 3. Okay. If over time is greater than 3, then leave, then else stay, right? Then we come in this part. This is the first level. Okay. This is the first level. This is inner nested if else. Correct? Can't we say that? Here we are going to say what? Here what are we going to say? That age is greater than 29 and less than 35, then they're going to else. Let me write here, stay, else. Right? We can write if else again. This is based on tree 1. Based on tree 2, we can write the if else again. Instead of keeping 35 here, we can put 29 first and we can say if age is less than 29. Okay. Then we go inside the else loop and we nested if else, and we are going to say if over time is greater than 3, then we say that it is leave, else it is going to, else people are going to stay, correct? And then for this one, the another part would be based on this age. It's going to say else if age is greater than 35, then people are going to leave, else they are going to stay. This is tree 2 and this is tree 1. Same problem, different trees we can make based on which rule comes first. Correct, right? Okay, understood? Now keep this thought in your mind. We'll revisit it. Keep this thought in your mind. Okay. Before we do that, I need to tell you a few things. Okay. Before we do that, I need to tell a few terminologies of your tree. Let me copy this out. Any tree we can look at. I'm choosing to take this tree, okay, to explain the terminologies. Let me make this bigger. We are going to look at terminologies. So this is called your root node. Okay, this is called your root node. Let me try to put it with a different color. This is your root node. This is what you call it, the first node of your tree. Okay, and all these which are in the end, they are called your leaf nodes or simply leaf. Okay, these are called branches. And what are these called? This one and this one. These are simply called nodes or internal nodes. Or simply nodes. Okay, this is your terminology of the tree. First is called root node. Then these are called your branches. These are called your leaf nodes, which cannot be, drill down further. You have already got to the final outcome. You have all the leaf, yellow dots here, all the stay green dots here separated, and all the green dots here, all the yellow dots here separated. You cannot further divide it. That is called your leaf node. Okay. Imagine this to be a tree opposite. If you have to remember this, imagine this to be a tree which is inverted. Here we have roots, right? And we have leaves on top, correct? At the last. Just imagine this to be opposite, rotated. You have the root on top and leaves at the bottom. Okay? There are no fruits in our tree. Okay. So now we have looked at what is decision tree, how we can make a decision tree, what are the terminologies of the decision tree. Okay. But tell me one thing, what were we trying to do? Let me try and copy this back again. What were we trying to do whenever we are trying to do classification as a matter of fact, whenever we are trying to do classification or any other problem, we are trying to do what here? Exactly. Tell me. We are trying to create a leaf which is homogeneous. We are trying to create a node, a leaf, which has all the yellow points together, all the green points together. There shouldn't be any mixture, right? It should be a pure node, correct? So the goal was to create homogeneous node, okay, or a pure node, correct? That was the goal. All yellow together and all green together. That was the goal, right? Because that's what you want to do. You want to separate out the greens from the yellow ones, correct? So the idea is that you need to reach to this pure node. You need to have a homogeneous mixture. Homogeneous is same type. Heterogeneous is different types. So how do we work from here? There is something called as entropy. Okay. There is something called as entropy. Entropy is nothing but measure of randomness. Okay. I'll tell you an example. Let's say you have this tree. Okay. And you have 200, your data has 200 samples. Okay. N is 200, out of which positive is 100 and negative is 100. Okay. Imagine it to be any example, but for now, just assume that you have, out of these 200, you have 100 in positive class, 100 in negative class. Okay. You have this, and you have some feature 4. You have made some rule. Okay. This is feature 4. Some rule you have made, and you get to these. Which is here you have, let's say you have 60 positive. Okay. Let me put it with a different color so that, and 40 negative. And here you will have 60 negative, correct? And let me also change this. Negative we are representing by green. And you will have 40 positive data points here. These are all your yellow points. Okay. Here you have more yellow points which are positive, and here you have a few green points. Here you have more green points. This is how your split is. Okay. This is some feature 4. Assume. Is this better? Okay. Is this better, or another tree which is giving you this? Let's say this is some other feature now, feature 3, because that's how we will get a change, right? So instead of having this now, you have 10 positive here, 10 positive, and you have 90 positive here. Let me do ulta because the dots are more there. 10 positive here, and you have 10 negatives here, and you have 90 negatives here. Which one is better? This is your tree. Let's say this is T1 and this is T2. Which is better, T1 or T2? Which is better? Anyone who thinks T1 is better? How did you decide T2 is better because it has more of, it can clearly say that in this part, 90 of them are belonging to yellow and only 10 of them are green, correct? Here, 90 of them are green and here 10 of them are yellow. But in T1, it was 60-40, right? Here I can be 90% confident. Let me write that. I can be 90% confident that it is positive class, correct? And here I can be 90% confident it's negative class, correct? Here, if I have to say the same thing, I can be only 60% sure that it's negative, correct? So I'm more confident in T2, right? So T2 is better. T2 is better. How did we decide that? We said that the randomness, the mixture in T2 is less compared to T1, correct? Right? That's how we decided. You only gave the answer, right? That T2 is better. How did we decide? We decided that the randomness, the mixture of yellow and green is more clear in T2 compared to T1. Ideally, it should be 100 and a 0, but in real life, you will not be able to do that, right? So 90-10 is really good. 90-10 is really good in this first level, okay? So that's where your entropy comes in. Now, this is your entropy. Now, formula of entropy, it will seem like a bit huge formula, but stay with me. We'll take it through, okay? And it will be really easy. Now, entropy, which is also defined as h of y, is nothing but summation of I is equals to 1 to k probability of yi, okay, log to the base 2 probability of yi, okay. This is the formula of entropy, okay. This is the formula of entropy. What is P here? P is probability, okay. What is K here? K is your number of features, number of categories, sorry. Here in our case, it was two. In the above case, it was two categories. One was positive, the other one was negative, okay. Log to the base 2 multiplied by probability of yi. These two terms are same and we have to sum it for all the categories, okay. We have to sum it for all the categories. Stay with me, okay. Stay with me. It will be super clear. We need to, no, you don't have to remember this formula. Sometimes our interviewer might ask, but you don't have to by heart this, okay. You only need to know what entropy is, okay. What entropy is, you only need to know that it is a measure of randomness, and measure of randomness meaning mixture, yellow and green point. Just remember this example and you'll get to know, okay. But since we're learning it, it's my job that I explain to you such that it sticks in your mind. You understand the concept. And for that, we need to look at the, formula. Let's consider an example here for entropy. Let's say you have a bag, okay. In there, you have 3 red balls and 3 yellow balls, okay. This is S1. And let's copy this. Okay, we'll do that later, but let's calculate the entropy. Now, what does entropy say? What is the value of K here? K is 2 categories, red and yellow, okay. And how many points do we have here? How many points do we have here? 6, right? So K is 2, N is equals to 6. And what is the formula? Formula is this. Let me write that here again so that it is easy to remember. Okay. Let me keep that here. This is your entropy formula. Now, how do we create this? We are going to sum this. We are going to create the entropy of S1 in this bag. What is the entropy? The entropy is, my bad guys, there is a negative here. See, even I forget. There is a negative here. Okay. So we are going to keep this negative outside and we are going to create the probability of, what is the probability of yellow balls. What is the probability of yellow balls? 3 by 6, correct? Is 3 by 6. 3 by 6 multiply by log of 2 multiply by log of 2 of probability of yellow. This is your yellow part. Okay, yellow category. Plus, what is the other? Red. Red is also the same. 3 by 6 log of 2, 3 by 6, right? This is nothing but, and this is your red category, red balls. So this will come down to 1 by 2 log of to the base 2, 1 by 2 plus 1 by 2 log of 2, 1 by 2. Okay. This is going to come down to log to the base 2 is nothing but log to the base 2 is nothing but what? Look at it. Okay. It is nothing but it is this is what you will get at the end. Okay. And what are you going to get out of this is you're going to get a +1. This entire term is going to come down to -1. Okay. So it is going to be -half and -half. This is going to be +1, minus minus plus. So the entropy of HS1 is going to be +1, means maximum. If we do the same thing, okay, if we do the same thing here, and I will say this to be S2. This is going to be S2, and we are going to have all the six balls as red. Then how do you think this will change? This is going to be S2. It is going to be what? Minus probability of 6 over 6 log of 6 over 6 plus, is there anything here? No, right? Category yellow is 0. So 0 multiplied by anything is going to be 0. So this is going to come out as minus, and log 1 is what we looked at in the previous sessions. Log 1 is nothing but 0. So again, 1 into some 0 is going to be 0. Okay. So you see here we have a homogeneous mixture and the entropy is 0. And here the homogeneous mixture is half. It's 50-50. The entropy is +1. So the graph of entropy is nothing like this. If we have the probability here, let this be a probability of 1, let this be a probability of 0, okay, and let this be 0.1, 0.5, okay, 50% probability, and this is your entropy. When we looked, it was 0.5, probability was 0.5 here, right? 50-50. Then your entropy value was 1, correct? And when the probability is 1, either all of them are 1, then it is going to be 0. And if it is 0, meaning no probability of yellow, it is again 0. So the graph looks something like this. So the graph, I don't want to draw this again. Let me change this to be 1. This is the graph of entropy. Okay. The idea is that you need to reduce the entropy. Okay. Correct. We need to remember, no, okay, I've already 100% read only. Exactly. So -1 next is going to be 0. So whenever you look at entropy, just remember this graph, it will help you. So the maximum value that entropy can take is 1 and the minimum is 0. Okay. Okay. Now let's take an example. We are going to create a decision tree from scratch. For you to understand how the algorithm works, it is always good to do a manual working. Okay, it is always good to do a manual working. So imagine you have this data set. Okay, you have few features here. This is your feature 1, feature 2, feature 3, and feature 4 probably. Okay, and then you also have your target variable, which is y, right? Okay, let's say the n is 1000 points. You have 1000 rows in your data frame. Okay, 500 of them are positive and 500 of them are negative. Okay, let it be 0, 1 or whatever. I'm saying positive or negative. Okay, now tell me one thing. We've already looked at the feature which tells you that, let's say there is this feature 4. Okay, there is this feature 4 which tells me this that I have, this is having 1000 data points here in the beginning, okay, which is nothing but 50-50. Okay, I've used it to get to this situation where now I have 800 total data points here. Okay, I have 800 data points here, out of which 300 are positive and 500 of them are negative. Then using feature 4, I am able to say that in this 200 of them are positive and 0 of them are this. This is one of my features, okay, using feature 4. The other option that I have, is of feature 1, where I say here at this end, I get 600 of them, okay. I get total 600 of them, out of which 400 are positive and 200 are 400 are negative and 200 of them are positive. Here I get ulta. Here I get that 400 of them are positive and 200 of them are negative, right? Now, tell me one thing. For the root node, if you were to make your, decision tree, will you pick feature 4 or feature 1? The first decision, which is helping you to reduce the entropy, which is able to reduce your mixture. Is it feature 1 or is it feature 2? I have to start making the tree. Okay. If I use feature 4, this is what I will get. If I use feature 1, this is what I will get. So should I pick feature 4 or feature 1? Okay. So let's change this. So let it be and 100. Now it's balanced. Right? Which one will you pick? So whenever you're creating this tree, how do you decide whether you take age 29, you take age 29 less than 29, age greater than 35? Any feature can become your root node, right? How do you start? You start it based on entropy. Okay. You try to pick that feature that is reducing the entropy to the maximum, meaning is reducing the entropy really good. That is going to be the first feature. So internally what happens is, it is the algorithm is going to look at feature 1. Okay, how much reduction in entropy do I get with feature 1? How much reduction in entropy do I get with feature 2, with feature 3, with feature 4? So that I am able to, divide my Y in a really homogeneous mixture. I'm able to reduce the randomness. I'm able to reduce the entropy. That is what we are trying to replicate here. We are trying to say, if I choose feature 4, this is what I will get. And if I choose feature 1, this is what I will get. Right? So we are going to choose feature 4. Absolutely. Right? So feature 4 will give us this. Feature 4 will give us this. This is what it is going to give us. So now, if you have to calculate the entropy, we had initially 500 positive and 500 negative. We got in here. How did we decide feature 1 and feature 4? How is the computer able to decide this? How is the algorithm able to decide this? Okay. Since we have already looked at, this is 50-50, right? This is 500 and 500. So what is the entropy here? Isn't the entropy here equal to 1 maximum? Right? Isn't the entropy here maximum? H is equals to +1, because we have 50-50 case. Similar to what we saw here, it was a 50-50 case, right? We looked at the graph also at 0.5, it is going to be 1 maximum. Okay. Here also at the starting, the entropy is +1. At the starting, you have this, the entropy is 1. But if you choose feature 4, okay, and if you do this, how do you get to here? The entropy here is what? The entropy here is 0. Entropy at this node is 0, right? And entropy at this node would be 3/5 into log of 2. into 3 by 5 plus 3 by 8, sorry, because we have total 800 points here, right? Plus it is going to be what, 5 by 8 into log of 2, log base 2, 5 by 8. Some value it will be, right? So that's how you choose your root node. How do you choose your root node? You choose your root node based on reduction in entropy. Reduction in entropy. And this is nothing but, this is called information gain. This is called information gain. Okay. How much of gain in the information are you getting? Here you are able to get more gain in the information. You're reducing the entropy more here, right? Here there is still some value. Here there is still some value. What's the value of this? Homogeneous, yes. So, okay. Let's do one thing. Let's do one thing. Can I create a new one from here? Let's try to create one here. New notebook. I need a new notebook. New notebook. So we have a new notebook. I'll tell you why I'm doing this. Okay. NumPy as NP. Let's run this. And then what was our this thing? It was 3 by 5 multiply by np dot log of 2, 3 by 5. Okay. And what do we have? So this is how even you can, calculate. I don't want to calculate it using the calculator. You already have NumPy. So here I have 3 by 8, right? I have 3 by 8. I have 3 by 8 here as well. Then the other point was what? 5 by 8. And this was also 5 by 8. Let's calculate. What is this? This is, I think there's something wrong. Shouldn't be negative. Shouldn't be negative. NumPy dot log 2, that's what we are using, right? Ah, okay, I get it. So the entropy is minus, right? So we have minus in the front. I get it. So in our formula, we already have a minus in the front, right? So that's why you're getting this negative. Let me fix all the comma brackets so that each of them is considered separately and the board mass is not applied. Okay, this has to be in a separate outside. It has to be this. Yeah, so it is 0.5. Let us go back here. So this value is nothing but this value is 0.95. Okay, so we had a negative in our entropy, right? This negative. So minus 0.95 into minus 1, this one into minus 1, the outside minus minus becomes positive, right? So that's how we are getting 0.95 here. Okay, now if you do the same thing here and the same thing here, let's do that. Let's do that. There's an important concept that I want to teach out of this. So let's copy this. Okay, let's put it here. And what is going to be here? It is total is 6. So it is going to be 4 by 6 and 2 by 6. Right? Right? So we are going to put that 2 by 6, 2 by 6. And here it's also going to be 2 by 6. Here 4 by 6, 400 and 200 was the split, right? So for that node, it's going to be 0.91. Okay. So it is going to be 0.91. What about this? Total is 400, right? Red is 300 out of 400. So 3 by 4 of a probability of red is 3 by 4 and probability of yellow is 1 by 4. So let's do that. Let's do this again. Let's put in here. And this is going to be 3 by 4 multiply by log base 2 3 by 4. Then this is going to be 1 by 4 multiply by log to the base 2 1 by 4, 0.81. Okay, so this is giving me 0.81, right? So now the thing is, how do you decide that the entropy has reduced. That the entropy has reduced. What was this is called parent. This is parent, right? And this is child. This is child. Both of these are child. Do we understand this? Right? Do we understand this? Right? We can say parent and a child. So how do we calculate? How do we calculate? How do I calculate? Now I know the entropy here is 1 plus 1 at my root node. Here the entropy is 0.95. Here the entropy is 0. But at this level it is 1. But at this level, how do I say? I have 2 children now. What do? I need to get the total entropy. What do I do here? What is the reduction? The reduction comes based on, you need to consider both the child. You can take an average, right? You can take an average sum of the child entropies. Yes, that is one example. That is one way. But how do we do this is we take a weighted average. Let me keep it here. Let me copy it. Let me put another one here. We take a weighted average. We take a weighted average. So rather than just summing them, we take a weighted average. So the total entropy at this level would be, or the reduction would be nothing but reduction in entropy is entropy of the parent, this one, minus entropy of the child, right? And for the child, since there are 2 child here, we'll have to take a weighted average. How is weighted average calculated? You know, here you have 800 points. Here you have only 200 points. So the weighted average entropy is multiplied by the number of observations that it is responsible for. So here it is going to be 1, since we have already calculated, minus, I'll keep it in the bracket. The first child is 0.95, right? Multiply by how many is it responsible for? How much is it responsible for? It's responsible for 800 over total 1000 plus 0 into this one is responsible for only 200 out of total 1000 that we saw in the parent, right? So this is going to be 0 and this becomes 1 minus what does this become, guys? This is going to be 4 by 5. Let's do this again to the numpy. This is 0.95 multiplied by 4 by 5. What does it give us? 0.76. 0.76. So the entropy is this. So the entropy is what? The updated entropy is 1 minus this is what? 0.24. Now, after dividing this, you are left with only such a low entropy. This is called your information gain. Okay. Whatever that you are getting by using. So what it does is internally, the model does the same thing what we did for only one feature. We did for feature 4. It does the same thing for feature 1, feature 2, feature 3, feature 4. So many features that you give, it will do it for that. And it will keep on try to, find which one should come here. Then after going here, okay. Then after coming here, it will try to look at again feature 1, feature 2, feature 3. We'll try to say, okay, which one is giving me the reduction in entropy? Put that rule here. Then it will again expand it further. Then if we have a pure node, it will leave it. If we don't have a pure node, it will try to divide it again based on features. Understood? How the features are being selected, which one to pick first, which one to put in the first here, then here, then here. Is that clear? It is based on reduction in entropy, and reduction in entropy is nothing but information gain. Okay. I know it is mathematical, but understanding this logically we understood that, how it works. It works on rules. It works on rules here, right? Go back. Yeah. It works on rules. It is nothing but if else, and it is axis parallel. But then how do we decide which feature to keep, feature 4 or feature 3? The one that gives us the pure node or is closer to the pure node is the one that gives us better and is going to be the one that we are going to start with. Okay. This is what we use. We use entropy. This is the formula of entropy. Then we looked at how does a decision tree make itself. First, it will select on feature 4 because it gives me the best entropy or best reduction. Then it will go to some other feature, then the third, then the fourth, until it gets everything sorted out. It will keep on creating this. It will keep on creating this. It will keep on creating this until it reaches a leaf node. Where it reaches, it will not do anything. But if it doesn't reach, it will keep on growing there. It will keep on going there like this. And this is also called your depth. So for trees, we say max, we say height. But here, since our decision tree is ulta, is inverse, so we called it as depth. Can we use this entropy concept to get which feature is useful? Not instead of adjusted R2, this concept, this entropy, when we go into the hands-on, you don't have to calculate it. It is already there in the algorithm. It tells you which feature is more important. It tells you which feature is more important. The one which is most important will be selected first, then second, then third, then fourth. So you can use this for finding the features that are important for any problem. Okay, you can get the importance of the feature, but not instead of adjusted R2. Adjusted R2, what it does is it tells that between this model and this model, which is a better model, it has that value, right? The one which is having a better adjusted R2 is a better model. But to pass the features inside the model, you can, of course, use this concept. And entropy is what is happening at a very minute level, at an algorithmic level. It is calculating those, information gains. But when you're using this algorithm in sklearn, in scikit-learn, it will automatically give you the feature importance. We'll look at it when we go into the hands-on. If this is clear, I promise to you guys, if this is clear, I promise to you guys, decision trees and random forests are going to be super easy for you, are going to be super duper easy for you. Okay, cool. We looked at reduction in entropy, nothing but information gain. Info gain is nothing but h parent minus h child. Okay, but since you have multiple child, you'll be looking at weighted average. Then all this comes down to information gain of which feature? Information gain of feature 4, which is 0.25. Okay, this is the entropy at this level total. This is the entropy at this level, which is 1. So parent minus child is 0.76. Now again, it will try to reduce from 0.95 to other. Okay. So basically, what do we get from this is that the feature, this is an important thing, the feature which gives the maximum, reduction in entropy, right? The one which reduces your entropy maximum is called your, first it will be chosen for root node, then doing all the other things also, like if it is in one internal node, from there you need to break in. Again, it will look at all the information gains, and the one that is giving you the maximum information gain, it will put that. Okay, and that's how you'll be creating your tree going forward and forward. Okay, information gain is nothing but reduction in entropy. Okay, this is really important. Okay, this is really important. Okay, so what it will do, it will try to look at IG of, where is our data set? To solidify all the things, I am putting this once again. Okay, let's copy this to solidify your understanding. This is what we are going to do. It is going to look at information gain of feature 1, information gain of feature 2, information gain of feature 3, information gain of feature 4. Then in our example, why was feature 4 chosen? Why feature 4 chosen? Because it gave the maximum information gain. Okay, that's how things work. Now you know that entropy is used and what information gain is, and you know that based on the information gain, you choose the feature that you want to split. Okay, splitting it is nothing but this question, that if else thing, you're here and then you're dividing it here. This is nothing but split. Okay, you're splitting the tree into two. Now what happens is, we also looked at that this is your depth. Now what happens sometimes you have, let me try to find an example if I can show that with an example. There was a beautiful example I looked at earlier. There is it. So just look at it. Okay, it tells us what is the root node, the topmost root. Okay, this is your decision node. You're trying to decide, any if or else, and this is your leaf node. Okay, to indicate the final one. Then we've already read this. You can, we've already covered this. Now it says that probably this is your data set. It has oak fruit here, which is in orange. It has cherry here, and it has apple here. Okay, everyone who is able to see the screen, everyone who understands what we are trying to solve, this dot, this size is nothing but the diameter that it is trying to show. Everyone who can see it, type a Y, type a Y, who can see this and understands the data set, what we are trying to do. Okay, cool. So now what do? We try to start splitting, and we say that if the diameter, in the first we had diameter less than 0.45, we say if the diameter is greater than equal to 0.45, we are able to identify all the oaks here. All the fruits that are oak are in this orange region. Okay, then we will do some splitting, additional splitting. Here we will do what? We will say our diameter is less than 0.32. Height is, first we will do, height is less than equal to 4.88. Here is 4.88. If it is less, then it is cherry, right? This purple color is cherry. Okay, and this is still some space where we have some things which are between purple and green, cherry and apple, right? So here we are trying to do some more decisions. We are trying to put some more criteria to split. We'll do some more splitting. How does it do? It is saying if now the diameter, this one again it is trying to put, if the diameter is greater than, is less than 0.32, less than equal to 0.32, then we have another decision to make. This is the region. Okay, but if it is greater than 0.32, this is what we get. We get apple. Then again it will try to break this height less than 7.714. This is 7.714, 7.14. Anything below that is cherry, anything above that is apple, right? So you see how many things it is trying to do, right? You see how many partitions it has done. Outliers, yes, there can be outliers. This one you're not able to identify, but it doesn't matter. It will still try to do some splitting based on it, right? So what does it say? The tree that we are seeing, this is the depth, right? 1, 2, 3, 4, 5. 5. This 5. We don't want to go this deep. We don't want to go this deep. Why? Do you see the problem with this? Do you see the problem that we will face if we go this deep? Depth is increasing. Yes, depth is increasing. But don't you feel that it is trying to create so many rules to find a pure node, right? To find a pure node, it is trying to do so many calculations, right? It is trying to do so many calculations to find the pure node. That sometimes leads to overfitting. How does it leads to overfitting? Let's go and check this out. Okay, let's go and check this out. Let me go back and open this. So here, let's see what they have done. They have they have taken this entire thing, right? Can I copy it? So basically, what I would have done, I would have not gone to so much of depth, right? I would have not gone to so much of depth. What happens is there is a concept of underfit and overfit. Okay. If you keep on increasing your tree, right? If you keep on increasing your tree, because ultimately it is an algorithm, it is a mathematics, right? It is going to look at a few things and say that, okay, I'm not able to do this. Let me go much deeper. Let me go much deeper. Let me go even more deeper. Probably going this deep is not right. You need to control this depth somehow. You need to control this depth somehow. I would have cut the tree here. You see, it is having 1, 2, 3, 4, 5, 6, 7. I would have cut the tree somewhere here. Okay. Why? Because if I keep on going till here, it will lead to overfitting. It will try to say that all my cherries are together, all my apples are together, all my, what was the other fruit? Oak are together. It will keep on dividing, it will keep on dividing. Even if this node, for example, has 9 cherries and 1 apple, it will still divide it further. But you can still stop there, right? You don't want 100%. What it will try to, what is overfitting? Overfitting is to exactly replicate the pattern of the data, right? What is overfitting? Overfitting, can I say overfitting is something like this? If I have a data set, which is like this, and the line that I'm trying to fit, or whatever non-linear thing that I'm trying to fit, if it goes and tries to capture all the points, isn't this overfitting? This is overfitting, right? This is overfitting. Correct? That's what it is trying to do here with all these trees. And what is underfitting? What is underfitting? Underfitting would be something like if I have my dots like this, I'm getting a line which is like this, or probably this again. I'm talking about all the non-linear combinations as of now. This is underfitting. It is not able to find the patterns only. That is underfitting. Overfitting is it is memorizing the patterns. It is fitting to perfectly. Okay. The idea of machine learning is that we create a model that is, you know, can be generalized. If your points are like this, okay, if your points is like this, then we are trying to build a model which fits the data like this probably. This is an outlier. Okay. This is something that we would prefer. General model. We are trying to create a model that is not affected by outliers, is trying to fit the model really well. This is what we prefer. And that is why we will try to cut this in between so that it does not overfits. And this process of cutting is called pruning. Okay. Why do we do this? Everyone understands underfit and overfit. Let me give you another example. Okay. Let me give you another example. We have 3 cases. Okay. We have already fit the model. And this is your model 1. Okay. This is your model 2. And this is your model 3. Okay. Then the train accuracy is 100%. Okay. And your test accuracy is 72%. Or let me create it more realistic. your train is 92%. Okay. And here your train is 52% and your test is 44%. And here your train is 81% and your test accuracy is 78%. Which one is a better model? Which one is underfitting? Which one is overfitting? Out of these, model 1, model 2, model 3. What is model 1? M3 is good. Yes. But what is M1? Is it an overfit? Is it an underfit? Is it a general good model? M3 is good. We understand. Everyone who understands M1 is overfit. Okay. Lakshmi says M1 is overfit. M1 is overfit. Ganesh also says M1 is overfit. Anyone else? That's right. That is right. You see what it is trying to do. The data set on which we trained, which was the trained data set, and we tried to, look at the accuracy on the trained data set only using the predictions on the train, it is getting 92%. But when we are trying to test our model on a data set that it has not seen in the test data set, it is performing so badly. This is an overfit condition, that it has learned so well on the training data set but is not doing so good on the test data set that is unseen to it. Here in M2, it is not doing good on the train also, and it is not doing good on test also. This is underfit. This is underfit. This is underfit. And this is your general model. You see, train is, yes, there is always going to be some difference between train and test, because test is something that you have not seen at all, right? So it is general fit or the right fit. That is what you're trying to do. That is what you're trying to do. Imagine you have created this. Okay. You have created this. Okay. Let us go to this exam. Let's go to this exam. Now imagine you have to do predictions now. Okay. You have to do predictions. You have already trained your data set. You have already trained your data set. This is your new data set. This is your new observation. How will you do prediction for this? How will you do prediction for this? Nothing. Just take its age, take its over time, pass it through here, ask the question that is it less than or greater than 35? It is greater than 35. So come here. Okay, come here. Then you will ask whether the age is less than 29. Is it? No. Then it will again come here. Then what does it say? It will say stay. So you know that for this point, prediction is so easy. Once you have trained the model, that's how you predict. When a new unseen data comes in, suppose this is in your test. Suppose this is in your test, you have to do the prediction. That's how you will train, right? If your model trains everything that is in your training data set, like this one, then what will happen if a new prediction model comes in here? What will it do? It will perform very badly, right? That's not what you want. That's not what you want. That's why we will try to do some pruning on this. We will do pruning on this. We will try to cut the tree. We will try to control the depth. That phenomena is called pruning. And pruning is done to what? Pruning is done to avoid overfitting. Okay? To avoid overfitting. Cool. That sklearn uses. And I'll tell you why, what the reason is also behind that. Okay? Let me just figure this out. So let's go to sklearn and let's pick up decision tree classifier. And yes, I think it's this one. Okay. Now you see, this is your decision tree classifier. Okay. It uses something called as criteria. Okay. And we looked at entropy. We looked at entropy to create the decision tree, right? There's something called as Gini. There's something called as log loss. Okay. And the default is Gini. What is this Gini? Okay. Then we also looked at depth of the tree, you have this something called as max depth. By default, it is none, but you can decide what depth you want to keep, for the decision tree. Minimum samples. What is this minimum samples? This minimum samples split, meaning how many samples should be there in a leaf node or a node for it to split again. Even if it says two, your data points are there, it will split again to 1 and 1. Ultimately, what it will try to do is it will try to put 1 and 1 in the leaf nodes. All the leaf nodes will have 1. Okay. So that's what you don't want to do. All these things you can, modify. These are the samples. But let me speak about this Gini. Okay. Let me speak about this Gini because this is most probably an interview question that a person will try to ask. Okay. Your interviewer will try to ask. Let me put down this as interview. Okay. There could be many questions based on whatever we have studied. There could be many, but majority of them could be what is entropy. Okay. That's what they will try to ask. What is information gain? We know what is information gain. Okay. We have already looked at it. Information gain. Then what is Gini? It is generally called Gini index or Gini impurity. And some people, some people say it is as Gini or Gini. Okay. So I call it Gini. I don't know why, but I call it. That's how I was taught, or that's how I learned. So it's all these things, they can call it as Gini index, Gini index. They can call it as Gini impurity or Gini impurity. Okay. All of them mean the same thing. Now, what happened? There's really an interesting story behind this. Okay. Let's look at Gini index or impurity. Let me write it completely so that you guys are not confused that it is Gini index and impurity are the same thing. It's Gini index or Gini impurity. Okay. Now, we have already studied entropy, which finds the randomness, correct? And we looked at the example that, the formula is I is equals to 1 to k, and it is nothing but probability of yi multiplied by log to the base 2 probability of yi. What happened? Now, all these algorithms, these decision trees, all of these, they have been laid out way earlier in 60s, 50s, 70s, 80s. Okay. They are being relevant now. Why? Because then we did not have the computation power. Now we have clouds. We have such fast GPUs, CPUs. Earlier, we never had those things. So, why people came up with Gini is because they thought computing this was little expensive. Computing a log of a probability took more time, was tedious, was, more expensive. So what they said that let us define another metric, which is Gini. Okay. Let me put it as Gini impurity. And it is nothing but it is very similar to entropy. It is 1 minus summation of I is equals to 1 to k. First part is same, probability of p yi to the square. Instead of calculating this log, what people did, they said, we will calculate the probability twice, no, and multiply it. Do you see how this is easier to calculate compared to log 2? All of the concepts that we have studied for entropy are same for Gini impurity. Nothing changes only apart from this formula. Nothing changes. If you have understood entropy, same thing works with Gini impurity. Nothing changes. We have to reduce the Gini impurity. That is called information gain. We calculated our entropy. We will also calculate our Gini impurity for selecting the root node, the one feature which gives us the maximum information gain or reduces the Gini impurity to the maximum. That is the feature that we're going to choose. Okay. To solidify this, nothing changes. Nothing at all changes. It's just that the formula is different. It's just that the formula is different. To solidify our, understanding, let us take this example. Let us take this example and try to calculate the Gini for this. Okay. We had these two, same as that. Even I feel, calculating Gini is easier because we don't have much. We have to only calculate, probability once and then, just put it in place. So example for calculating Gini impurity or Gini index. What was the issue here? So we have to calculate 1 minus, I'm taking this inside, it is 3/6 probability square plus 3/6 square, right? What does it become? 1 minus, this will become 1, right? Why? Because it is 1 minus probability of red ka square plus probability of yellow ka square, means 1 minus, what does this become? This is going to be 1/2 square plus 1/2 square, which is nothing but 1 minus 0.25 and 0.25. This will come out to be 0.5, right? And here, what will this become? This is going to become, let me write it properly here. So the Gini impurity for S1 is 0.5. Okay, from here. And Gini impurity here will become what for S2? 1 minus, what is this? Probability. What is the probability here? 6/6 square plus 6 on, there's nothing here, 0, right? Probability of yellow is 0. So this becomes 1 minus 1 square, nothing but 1 minus 1. So the Gini impurity here is for S2 equals to 0. Okay. So what did we notice? What did we notice? We noticed that entropy can take a range from 0 to 1, whereas Gini impurity can take a value from 0 to 0.5. That's the only difference. Rest everything is same. Rest all the things are same. Let me try and see if we can get an example. It is entropy and Gini graph. Why is my, there you go. Okay. So this is your graph for both Gini as well as probability. So what did we notice here? That here the maximum value that it can take is 0.5. And what is the maximum value that it can take is 1. For what? This is 0.5. Okay. And this is only probability and this is only impurity measure. All the working is same, is just that your scikit-learn uses Gini impurity as a default. Whatever we studied from entropy is what was used earlier. And why did they come up with Gini? Because it's easier to calculate, right? And it's also easier to remember. So probably this is something that you can expect in your interview. Can expect this thing in your interview. You can also expect some of the other things. Is that, what did we look at? How splitting is done. How splitting is done. Okay. Then how root node is selected. All the terminologies that we looked at. Meaning, what is root node? What is leaf node? Okay. Then what is information gain? What is Gini index that we already have put in there? What is underfit? Okay. Then what else? What else did we look at? All the things that we have studied together here is everything that is important. Everything is important, whatever we have run, studied together. Because trust me, guys, in the industry, these decision trees and random forests are used heavily, and they are really good. Okay. So you need to be very clear with this concept. Okay. Thank you.
Hi guys, here we have just covered the theoretical part related to decision trees due to the time constraint. We have covered the decision tree implementation part in this separate video. Please check it out by clicking on the I button right now. Moving on, we'll take you through top 15 machine learning interview questions right away.
So let's begin with our very first question, which is what is machine learning and why is it important? Now, as you can see in this diagram, machine learning is a part of artificial intelligence, right? Under machine learning, we have concepts like neural networks and deep learning, right? Machine learning basically consists of dozens of different machine learning methods or algorithms, which we will be covering a few in this particular video throughout our questions. So machine learning is basically teaching computers to learn on their own, right? So what machine learning basically does is it will show the computer hundreds of pictures of, say, apples and oranges. Okay, so machine learning is basically going to pick these two fruits and show them to the computer. Now what machine learning is doing here is basically it's not telling that apples are going to be red and round. Similarly for oranges, that they're going to be orange in color and they're also going to be round. Instead of giving certain rules, it is going to let the computer figure it out by itself. It is going to go through the hundreds of images and going to figure out a pattern by itself. So this way, whenever a new kind of apple or a new kind of orange is shown to the computer, it is going to be able to figure them out. So this is the basic idea behind machine learning, right? So it basically reduces the repetitive manual work. Like, so say you want to filter out the spam emails, right? So you do not need to do that manually. Rather, machine learning is going to do that for you based on certain keywords. So basically, if an email contains words like free and offer, so keywords like that, so based on that, machine learning is going to help you identify that these emails could be spam. So machine learning reduces repetitive manual work. It helps businesses make data-driven decisions. It powers personalized recommendations like Netflix and Amazon. So you guys must have noticed every time you open Netflix, you will be suggested some movie or the other, or some series or the other based on your previous watches. So that is again machine learning behind. It drives innovations like self-driving cars and medical diagnosis. So again, it is not just limited to the basic applications we see like Netflix. In fact, it is seen everywhere like self-driving cars and medical diagnosis as well. So our second question is differentiate between supervised, unsupervised and reinforcement learning. So first let's go to supervised learning. So as you can see over here, we have some raw data, and whatever algorithm we apply, it is going to have labeled data. This is basically supervised learning over here. This is the major point, that we're going to have labeled data. And then we're going to have a prediction. So now let's look at that in detail. So supervised learning, one of the three types of machine learning models, is when the model is given labeled data. That is your input and the correct output. You have it labeled. Your algorithm knows that this is the input I'm getting and this is the output that is supposed to be predicted, right? It is going to learn the relationship between the input-output to predict the future results, right? It is used for tasks like, say, classification and regression. Classification is, say, your spam or not spam emails, and your regression could be predicting your house prices, right? So basically what supervised learning does is it learns from the examples and it predicts the answers for new unseen data. Right, another example you can consider is we give labeled photos of cats and dogs. Right, we give photos and we label them as cats and dogs. Now it is going to learn to identify animals as either cat or dog in the future pictures. And since we have already told the algorithm when we were giving our data that this is a cat and this is a dog, this makes our data labeled, right? So this is all about supervised learning. Then we have unsupervised learning. Now whenever we give our raw data, it is going to be unlabeled. So this is the major difference between supervised and unsupervised learning. Let's look at it in detail.
So basically, unsupervised learning is, if you were to consider a real life analogy, a student solving problems without a teacher, right? So it is doing everything on its own. So no answers are provided. The student, or you can say our algorithm, has to find patterns or similarities on its own. So basically, unsupervised learning is when the model is given data without labels and must find patterns or groupings on its own. Now, in this case, we just have given some random pictures of animals. And now our algorithm, that is our unsupervised learning method, has to figure out on its own which one's a cat, which one's a dog, or maybe it is going to group similar pictures together, and then we can identify a pattern between them. So it works like that. So the model basically doesn't know the answers beforehand. It tries to group similar data together, like clustering customers by their buying habits, right? So it is going to find a common pattern between the data, and it is going to try and group them together. That is what unsupervised learning basically is. Moving on to a third type of machine learning model, which is reinforcement learning. Now, reinforcement learning works like, say, you're teaching your pet dog some new tricks. So whenever the dog is going to do something right, or it is going to get the trick right, it is going to get a treat. And if it is not able to perform that particular trick, there will not be any treat, or you can even introduce some sort of penalty. So that is the same way reinforcement learning works. So whatever agent you have, it is going to learn through interacting with the environment, right? So if the agent gets the action right, there's going to be a reward, or there could be a penalty for getting anything wrong, right? So let's look at it in detail. So the model learns through trial and error, trains software to make certain desired actions, right? So you can say like a robot who is left out in the open is going to interact with its environment, and through trial and error, it is going to learn what actions lead to rewards and which ones lead to penalties, right? It is going to learn by interacting with the environment. It gets feedback in the form of rewards and penalties. So that is basically how reinforcement learning works. So we have a table over here differentiating the three based on data, goal, and an example. So you can say supervised learning is labeled data, unsupervised has unlabeled data, and reinforcement learning learns by interaction with the environment, right? Then there's the goal. So supervised learning has the basic goal of learning the mapping between the inputs and the outputs. Unsupervised learning finds patterns and groups the similar data, whereas reinforcement learning maximizes the rewards by trial and error. Then we have our example. Supervised learning could be classifying emails as spam or not spam. Unsupervised learning could be clustering the customers based on a particular habit or behavior. Then reinforcement learning would be training a robot to walk, right? So moving on to our third question, what is a model in machine learning and how is it used? So a machine learning model is like a recipe, you can say, or a set of rules that basically helps the computers to solve the problems. It's built by learning from data and figuring out the patterns. So basically you have your training data, you extract patterns from the data, and then you use those patterns to predict the results. That is basically how you evaluate whatever you have trained your model on, right? So a machine learning model is, as we discussed, a set of rules or instructions created by learning patterns from the data. It is used to train data to make predictions or decisions, right? So say for example, you're training a student. So when you give that student a textbook, so the student is basically going to study from the textbook and answer the questions based on that, correct? So that is similarly how machine learning models also work. They basically study from the training data that they receive, and then they implement whatever they have learned, whatever patterns they have figured out from the training data set, they implement it on their test data set or whatever new data they receive, and then go ahead with the predictions, right? It is used to understand relationships, classify things, or predict outcomes. So basically there are two steps. First is training the model. The model learns from examples or the data to understand patterns. This is your training data. For example, feeding the model pictures of animals labeled as dog or cat. That is your training data, right? You're giving your algorithm, your model, some sort of data, and you're telling that this particular image is of a dog, this particular image is of a cat. Now it is your duty to understand it, to understand why this is a dog, why this is a cat, and then you test it or you make predictions right? You are going to show a new picture that the model or your algorithm has not seen previously, and then test it whether the model is able to predict the right answer or not, whether it's a cat or a dog. So that is basically how a model works, right? Moving on to our fourth question, explain overfitting and underfitting with examples. Now let's first look at these diagrams over here. So basically what these dots are your data points, right? You can see all these dots, these are your data points. Now in your first graph, you have a straight line going through the data points, but not really covering or not really touching a lot of them. So this is what is called as underfitted or underfitting, right? Then you have this image over here where your line is basically trying to touch every single data point that is there. This scenario is called overfitted. And then you have your middle image where your line is trying to find a middle path where it doesn't really touch every data point and it does not also exclude all the data points or is not too far away from all the data points, right? So this is called a good fit or a robust fit. This is what we ideally want. And these are the two conditions that you want to avoid. So now let's go ahead and look at them in detail. So overfitting basically happens when your model learns the training data too well. Now, say for example, you are preparing for an exam and whatever materials you have, so instead of understanding the concepts, you try and by heart every single example, every single definition that is given to you in your material. Now, if in the exam you get the exact same questions with the exact same numbers, you are good to go, right? You are going to know every answer because you have by hearted, you have memorized them. But in case you get some unseen questions, that is the time you're going to suffer. So that is basically overfitting. What overfitting is doing here is basically it's trying to memorize each and every data point in your data set, right? So in this case, whenever a new data set is given to your model, it is not going to perform very well, right? It is going to perform very poorly on unseen data. Why? Because it captures all the noise and the irrelevant details. So say for example, you're training a model to classify dogs and cats. If it is overfitted, it is going to learn that cats only have one specific background in the training images. It is going to capture that maybe all the cats are white or some unnecessary detail, right? And whenever you're given, say suppose you give a picture of a white dog, your model is going to classify it as a cat because it has learned or it has memorized that this particular image or this kind of image belongs to a cat. So that is what overfitting means. Then you have your underfitting. This occurs when your model is too simple. Like we saw in this diagram, when you have an underfitted model, your line is not really going to care about the data points as such. It is going to oversimplify the things and fail to capture the underlying patterns in the data, right? As you can see in that diagram, the line is not particularly capturing any sort of patterns. So this leads to again poor performance on both the training data and the new data. Now if we were to consider the example of a student again, so now in this case what the student is doing is he is basically skimming through the pages, just reading the headlines and moving ahead, thinking that he has learned everything about the topic, right? So this is underfitting. Now a model which is meant to classify cats and dogs is going to be underfitted if it predicts every animal as a cat because it hasn't really learned the difference between features of dogs and cats, right? So that is what underfitting means. So here we have a table differentiating overfitting and underfitting. So performance on the training data for overfitting is going to be excellent, whereas for underfitting it is going to be poor. Performance on the testing data is going to be poor for the overfitting models, and for the underfitting model it is also going to be poor. Now as you can see, the underfitting models are going to perform poorly no matter whether it's a training data or a testing data. Why? Because they do not really capture any sort of patterns right from the beginning. So even on the training data, they're not going to perform well. Whereas overfitting is going to do exceptionally well on the training data, but it is going to fail to perform well on the testing data or with whatever new data that is presented to the model. So then we have our model complexity. So overfitting is going to be too complex because as we discussed, overfitted models literally try to learn every single detail of the model or of the data set. So it is going to be way too complex, whereas underfitting is going to be way too simple because they barely capture any details or they barely try to understand any sort of pattern, So the solution is to simplify the model, use regularization, or get more data. Whereas in underfitting models, you can use a more complex model or tune the parameters, right? So reading these points, you must have gotten an idea that what is important is a balance between the two to achieve a good or a robust model, right? Your model shouldn't be overfitted or underfitted. That is, it shouldn't be too complex or it shouldn't be too simple. It should be just midway between these two to achieve the best balance, which is also known as the bias variance trade-off, right? You can also mention this point because, let me just write it down. So it is also called the bias variance trade-off, right? So moving on to our next question, what is a confusion matrix and how is it used in evaluating the models? Now, a confusion matrix is basically a table that helps you to evaluate how well a classification model is performing, right? So it compares the model's predictions with the actual outcomes. Basically, whatever predictions your model is going to make, you're going to have some correct values, you're going to have some incorrect values or incorrect predictions. So all that is mapped in a very organized way and shown in a table which is called the confusion matrix, right? So it is useful for understanding the types of mistakes your model is making. So this is what a confusion matrix looks like. You have your actual values, that is, say you have your training data and your testing data. Right. So for your training data, you have your actual values, that is, say you have a column predicting yes and no, right? So it basically goes like this, yes, no, yes, no. Whereas your testing data is going to predict something like yes, yes, no, yes, right? So as you can see over here, this particular prediction is correct over here, whereas all these are wrong, right? This was supposed to be no, this was supposed to be yes, this was supposed to be no. So all this can be mapped in a very organized way, as you can see over here. So our actual values are here and our predicted values are here. So if our actual value was positive and our predicted value is also positive, we call it a true positive. So this is basically a correct value. But if our actual value was positive but our predicted value was negative, we call it a false negative. That means this value is incorrect. But if our actual value was negative and our predicted value was also negative, we call it a true negative. That means it is correct. But if our actual value was negative and our predicted value was positive, we're going to call it a false positive. That means it was incorrect. So this is basically how a confusion matrix maps out all your predicted and actual values to help you analyze how well your model is performing and how much of your predictions are correct and where exactly your model is making mistakes, right? So true positives, we just discussed. The model correctly predicts a positive outcome. False positive is when the model incorrectly predicts something as positive. This is also known as a type 1 error. Then you have your true negative. The model correctly predicts a negative outcome. False positive is when the model misses a positive case and instead predicts it as a negative. So that is called a false negative. Alright. So now that you have understood what is a confusion matrix, let us also see how it is used in evaluating the models. So for evaluating the models, we use terms like accuracy, precision, recall, and the F1 score. Now, accuracy basically means the overall correctness of your model. This is what accuracy is going to test. Precision focuses on how many of the predicted positives are actually positives. Recall focuses on how many of the actual positives are correctly identified. And F1 score is basically a balance between precision and recall. So you can give an overview of how these terms, you can also go ahead and explain the formula for these particular metrics, right? So that was all about the confusion matrix. Let's move on to our sixth question, which is define cross-validation. Now, cross-validation is nothing but a method that is used in machine learning to test how well a model will perform on unseen data. So how is it going to test? it is basically going to split the data into multiple parts. So say you have a data containing 50 rows. So what this cross validation is going to do is it is going to split the entire data set into say 5 rows each, and it is going to create 10 parts of such 5 rows, right? So it is going to train the model on some parts and test it on the remaining parts. So that is basically how cross validation works. Now this ensures model performs consistently. So it is going to prevent overfitting, it is going to have a reliable testing, and it is also going to maximize the data usage, right? So as you can see, cross validation has split this particular data into 5 parts, right? So what cross validation is doing here is it's going to train the data on these 4 parts and then test it on this 5th part. And it is going to do that until and unless each and every part of it is tested, excluding the remaining 4. As you can see, at the second time, it is going to train the data on these 4 parts and then test it on the 4th part over here. Then it is going to test it on the 3rd part, then on the 2nd part, and then on the 1st part. Basically, it is going to create a combination for all the number of parts that it has created for the particular data set. Now, this is going to ensure that our testing is reliable. So this also prevents overfitting and it maximizes the data usage. Now consider this example where say you're preparing for a spelling bee competition. Now you have a list of 100 words that you need to prepare for. Now instead of testing on the entire list of these 100 words, what you are going to do is you're going to split these 100 words into 10 smaller groups, right? So you're going to have 10 lists, each having 10 words, right? So now you're going to study these 9 groups and then test yourself on the 10th group, right? Now you're going to repeat this process until you have tested yourself on every group. The next time you're going to go ahead and practice on the first 8 and the 10th group and then test yourself on the 9th group. So this is exactly what cross validation is doing in this case, right? So make sure whenever you go in an interview, you give relevant examples and you are very clear with your explanation so that the interviewer understands that your concepts are clear, right? So moving on to the 7th question, what is the role of precision and recall in evaluating a model? Now let's understand this diagram first. So basically we have our spam emails over here in this section and we have our not spam emails in this section. Simple. Now what our algorithm is doing is, it is predicting all these emails as spam. Now as you can see, the green section is correct because it is correctly identifying these spam emails as spam. Now but the red section over here is that the not spam emails are also classified as spam. So basically what our recall and precision is doing is, our recall is going to test all our true positive, that means all the correctly predicted spam emails as spam based on our spam emails. So precision basically measures how accurate the model's positive predictions are. So in other words, you can say that all the predictions the model made as positive, how many were actually correct, right? So basically it is going to compare these two sections. Now say for example, you have 10 emails in total and 8 of them are actually spam. So in this case, our precision is going to be 8 upon 10. Alright. Now let's look at recall. So now recall basically measures how well the model identifies all the actual positives. So it is basically going to compare this entire section, right? As you can see in this image. So out of all the spam emails, how many did the model catch? So say we have 20 spam emails. Alright, and the model actually figured that 8 of them were spam. This is a prediction, right? So our recall is going to be 8 out of 20. This is what the recall is going to measure. So both these metrics work on true positives, false positives and false negatives. So again, we will have to use a confusion matrix in order to calculate these. Right, this is the formula for precision, true positives upon true positives plus false positives. Basically trying to predict how many of the predicted positives are correct. Right. Then for recall, we have true positives upon true positives plus false negatives. How many actual positives were identified correctly. Right. So a precision and recall basically give the insights beyond the overall accuracy. Now, if your model has a very high precision, your model is basically trying to avoid the false alarms. Basically, that means very few false positives. Whereas a high recall is going to minimize missed positives, that is, very few false negatives. Now, these criteria are very important. Let us quickly look why. They are especially important when the cost of errors vary. Now, consider a scenario of a medical diagnosis. Now, missing a disease, that is a low recall, is going to be worse than a false alarm, right? In cases of medical diagnosis, you're going to prefer that if there is even a slight chance or a slight possibility that a person could have a particular disease, you would prefer a medical diagnosis in that case. Rather, missing that particular disease and hence not going for the medical diagnosis is going to be worse in this particular scenario. Whereas another scenario where you are detecting spam emails, so in case you flag the genuine emails as spam, now say for example you have a very important email and you flag that particular email as spam, which is in the case of low precision, it can be annoying or it can even cost you, say, a missed opportunity. Right? So you need to consider these scenarios in mind and choose which metric, it could be precision or recall, which one you need to be higher in which scenario, right? So moving on to our 8th question, what is the F1 score and how is it calculated? So the F1 score is basically a metric that combines precision and recall into a single number. Now, just as we discussed the two scenarios where a high precision or a high recall is going to be beneficial in one case, whereas so the F1 score is basically a metric that combines precision and recall into a single number. So it basically provides a balance between the two, right? Precision and recall. Now, just as we discussed in our previous slide, the medical diagnosis and spam detection situation, where keeping one variable low and the other high is going to be beneficial in one case, whereas it could be harmful in the other. So in cases like this, we need something that is known as the F1 score, which does nothing but provide balance between these two metrics. So the F1 score basically ranges from 0 to 1, where 1 indicates perfect precision and recall. So if you achieve your F1 equal to 1, that means you have a perfect balance between precision and recall. So this is the formula for your F1 score, twice into precision into recall divided by precision plus recall. So F1 score is, like we discussed, very helpful when your precision and recall are in conflict, right? Right. So that is all about F1 score. So moving on to our 9th question, what is the purpose of regularization in machine learning? So regularization is basically a technique that is used to prevent overfitting by adding a penalty to the model's complexity during training. Now it adds this penalty to the loss function during training, right? This prevents overfitting. Now overfitting occurs when a model performs well on training data but poorly on unseen data, as we already discussed previously. Right, so regularization is going to help the model generalize better on new data. So basically it's a technique that is used to prevent overfitting. That is the main criteria. Now there are two types of regularizations, that is L1 and L2. L1 is called the lasso technique and L2 is called the ridge. So as you can see, without regularization we have an overfitting where our line is trying to touch each and every data point. Whereas after regularization, we're going to have a better fit where our line is more generalized. It is near all the data points, but it is not really memorizing any data points as such. So the L1 or the lasso regularization is basically when it shrinks some weights to 0. Basically, it tries to remove the irrelevant features and it tries to make the model more simpler, right? Whereas the ridge regularization focuses on reducing the large weights. It encourages the model to balance the complexity without exactly eliminating any features, right? So basically, regularization reduces overfitting. That is, it prevents the model from becoming too complex, right? Or we can say it reduces the complexity. reduces complexity. We've already seen how. It simplifies the model. It basically encourages more interpretable weights, right? It improves generalization. That is, it makes sure that the model performs well on unseen data as well, right? So the training as well as the testing data is focused over here through generalization. Then we have multicollinearity, that is the high correlation among input features. So say we have two features, that is number of bedrooms and number of bathrooms. So if these two features have a very high correlation, there's going to be a problem in simple models like linear regression, right? So this multicollinearity problem needs to be handled, and it can be done through regularization. So these are the benefits of regularization, and I hope you guys understood it and will be able to explain it in an interview as well. So moving on to our 10th question, explain the bias variance trade-off. So the bias variance trade-off is basically the balance between two sources of error in machine learning, bias and variance. So we have already discussed underfitting and overfitting. Underfitting, and let me write overfitting over here. Right. So underfitting basically occurs when we have a very high bias, whereas overfitting occurs when we have a very high variance. Right. So now in order to find a balance between underfitting and overfitting, we have something known as the bias variance trade-off. Right. So as bias decreases, variance increases, and vice versa. So this is how these two variables are correlated. Alright, let me just clear my screen. Okay, so now the goal is to find a balance where both bias and variance are minimalized for best generalization. Now we do not want any of these terms to have a greater effect on our model. So we're going to have to minimize both of these terms to achieve a better generalization. Right. So as I already told you, if we have a very high bias, our model is going to be too simple, that it is going to be underfitted, right? And if we have a high variance, that is, a model is going to be too complex. We're going to have a good accuracy on our training data, but a very poor performance on our testing data. So that is what high variance does, or overfitting does, right? So consider an example where you're hitting a target. Now, if you have a very high bias, your arrows are going to land very far away from the target, but in a very consistent, or you can say systematic error, right? Either they're all going to go, say, towards the right direction. But in case of a high variance, your arrows are going to scatter unpredictably, right? One arrow could variance has been minimized. So that is all about bias variance trade-off. Moving on to our 11th question, what is feature engineering and why is it crucial in machine learning? So you can see in this diagram, we have raw data, and then we have something known as feature engineering, and then we come to our ML model. So now what feature engineering is, it's basically involving refining or creating input variables to make them more useful for a machine learning model. Right, in order to implement a model on your raw data, you need to have a well-refined, or you need to have your input variables that are very useful. So that is done through feature engineering, right? So feature engineering basically involves steps like feature selection, feature transformation, feature creation to improve a machine learning model's performance. So feature selection is where you pick the most important features for your model. So say in a house price prediction model, the area of your house is going to be more relevant than the color of the house, right? Then comes feature transformation. So this involves modifying features to make them more suitable for analysis, such as you can say normalizing your numerical data or encoding your categories, right? So basically you transform your data into a more useful format. Then you have creating input variables or features. So this is basically called feature creation. This is where you create new features from the existing ones. So say for example, you combine the height and weight into a BMI feature or a body mass index, right? So that is called creating your input variables. So the benefits of feature engineering are model accuracy improvement. So by providing the model with the right information, you improve the accuracy of the model, right? Then comes reducing the overfitting or preventing overfitting. This is done by focusing on relevant features, right? So once you reduce the noise or the irrelevant information like color of the house, automatically your overfitting is reduced. Then comes simplifying models. Now, when you eliminate the unnecessary complexity, your model automatically becomes simplified, right? Then your final advantage is highlights the domain knowledge. Now, when you perform feature engineering, it incorporates domain expertise, right? If you have a good domain knowledge, you can make your model much smarter and you can tailor it to the problem, right? So again, feature engineering has a advantage of highlighting your domain knowledge. Moving on to our 12th question, example of when a false positive is more crucial than a false negative and vice versa. So this scenario we have already discussed, but let's look at it in detail. So we know a false positive is when a model predicts something as positive, but it is actually negative. Example, a fire alarm going off when there is no fire, right? Then we have a false negative when a model predicts something as negative, but it is actually positive. So this is missing an actual fire when it occurs, right? So there is a fire, but you missed it. You predicted it as negative, like there's no fire, but in actual there was a fire. Basically, that's what it means. So now that we have covered what is false positive and what is false negative, let's look at an example or a scenario where one is more important than the other. So let's look at the scenario when a false positive is more crucial. So in case of a spam email detection, what a false positive is going to mean is basically you classify a legitimate email, that is an important email, as spam, and now what the consequence is going to be is it is going to get missed by the user. It could be a job offer or a client communication letter. It could be any sort of email. And a false positive is going to mean is that important email is going to get classified as a spam, right? So this is where a false positive is very crucial. You cannot just blindly mark any email as a spam. Then you have your false negative. So in case of a cancer detection or any say medical diagnosis. Right, so a false negative is going to delay the diagnosis and the treatment, which could be life-threatening. We've already discussed. So the model is basically going to fail to detect cancer in an affected person. So this is where a false negative is crucial. Moving on to a 13th question, what does naivety stand for in naive Bayes, right? So naive Bayes is again a machine learning algorithm based on the Bayes theorem. Now this is used for the classification task. Now what the naive stands for in naive Bayes, basically it refers to the assumption that all the input features in your data set are independent of each other, which is again not true in the real world, right? Now say for a house price prediction model, you cannot have a number of bedrooms and the number of bathrooms or number of bedrooms and the price feature as independent variables. They cannot be independent of each other because obviously each of these factors are interrelated and are going to affect each other, right? If you have lesser number of bedrooms, your price is definitely going to be affected, right? So it is not true in the real world, but it is an assumption made in machine learning whenever we use naive Bayes, that all the assumptions, that all the input features are independent of each other. So basically this is how the Bayes algorithm works. It basically classifies all or basically groups the different items into different groups, and this is the formula for the Bayes theorem. So we already saw naive Bayes assumes that changing one feature is not going to affect the others. This is the independence assumption. We have already discussed this. Now this works well with limited data, mainly for one reason, because it does not really need the complex relationships between features, right? So it is again fast and efficient, that is, it makes the computation really efficient. Then again, it is surprisingly accurate, even though in the real world, the assumption that the naive Bayes algorithm considers is not true. It is surprisingly accurate in machine learning. So basically, even in the example we discussed, So even when the independence assumption is violated, it will still provide accurate predictions for many tasks, right? So that is one advantage or one very important characteristic of naive Bayes. Moving on to our 14th question. Give an example where the median is better measured than a mean. So now we know mean is basically when you add up all the numbers and divide by the total count, right? So say for example, you want to find the average of 2, 4 and 6. You're going to add 2, 4 and 6, and since the total count of these numbers is 3, we will divide by 3 and our answer is going to be 4. Whereas median is basically finding your middle number when all the numbers are arranged in a particular order, right? They need to be in a descending or an ascending order, and whatever middle number you find is your median. So the median of 2, 4 and 6 is going to be 4. This is the middle value, right? So now when does median outperform mean? Now when do we prefer using a median rather than a mean? So consider a scenario where you have 5 people and you're given their incomes. First is 30k, then you have 35k, 40k, 45k, and then you have 1 million. Now you can notice that these 4 numbers come in a very close range, whereas 1 million lies in a very far range. That is, this particular number is an outlier, right? So if you were to plot these numbers in a graph, 1 million would stand out compared to the rest of the numbers, right? So that is basically what outlier means. So if we were to find the mean of these particular values, we would have a number something like this. This is not accurate, because if we were to find the mean for these particular values or these particular incomes, we wouldn't have such a huge mean, right? Our mean has been changed, or it has been influenced because of this particular outlier. So in cases like this, where we have a heavily skewed data, this is when median is more efficient. Now if we were to find the median for these particular values, it would be 40k, and this would represent the income of these 5 people more accurately, right? So basically median is not affected by the extreme values or the outliers, as we just saw in this particular example, right? So it gives a more realistic picture whenever data is skewed, like in income or in property prices, right? So whenever you have a high range of your data, you're going to prefer median over mean. Moving on to our 15th question, what are the key differences between bagging and boosting in ensemble methods? So let's understand what is bagging first, right? So bagging basically stands for bootstrap aggregating. Now this creates multiple models by training them on different random subsets of the data. Now each model makes a prediction and their results are averaged for regression or voted on for classification. Now example of bagging is random forest, right? Now in case you're not familiar with ensemble methods, let us quickly discuss ensemble methods. So ensemble methods are basically like building a team, right? Multiple models or players, they all come together to make better predictions. So all these factors coming together basically reduces the errors and increases the stability of the model. So bagging or bootstrap aggregating, let's consider an example to understand it better. So imagine you're dividing your classroom into groups and giving each group a problem. Now whatever answer each group comes up with, you average their answers. Now this method is going to reduce the variance, and it is also going to make the final model more stable. Now random forest is a classic example of bagging. Then we have boosting. Now boosting takes a little bit of different approach. Now models are trained one after the other, with each new model focusing on the errors made by the previous one. So instead of combining the models simultaneously, boosting is going to combine them sequentially. Here each model is going to correct the errors of the previous one. So the boosting algorithm basically corrects the errors or improves the mistakes as the algorithm moves forward, right? The examples of boosting algorithms are the gradient boosting or the adder boost algorithm. So let's understand boosting by an analogy of real world example where a teacher is helping the students who struggled the most in the last test. So now boosting is going to be a very great way of correcting the bias in weak models, right? So whichever students struggled in the last test are going to be trained separately and help improve their performance in the next exam. So this is exactly how boosting also works. Let's quickly look at the difference between bagging and boosting methods. So bagging basically works in a parallel method where models are trained independently, right? All of the models are being trained at the same time independently. That is, they do not have any sort of connection between each other. Whereas boosting works sequentially. Models depend on each other, where one model corrects the mistakes of the previous model. Bagging focuses on reducing the variance, whereas boosting focuses on reducing the bias. Bagging treats all the data points equally, whereas boosting focuses on correcting the errors only. Bagging is less complex, whereas boosting is more complex due to the dependency. Bagging is good for stable models with high variance, whereas boosting is good for weak models with high bias.
Just a quick info, guys. Intellipaat offers an executive postgraduate certification in AI and machine learning in collaboration with iHub, IIT Roorkee, and Microsoft. This comprehensive course is designed to make you an expert in AI and ML in just 11 months by working on over 50 real-time projects and industry case studies. With this course, we have already helped thousands of professional and successful career transition. You can check out their testimonials on our Achievers channel, whose link is given in the description below. Without a doubt, this course can set your careers to a new height. So visit the course page link given below in the description and take a first step towards career growth in the field of AI and ML.